Picture this for just a moment, a world where the sky is painted with the light of two suns, casting long, shifting shadows across an alien landscape, or an ocean, not of water, but of churning, molten lava, glowing with an unearthly fire under a sky filled with unfamiliar constellations. These aren't scenes from science fiction. These are real places, worlds orbiting distant stars, and they represent one of the most thrilling quests in human history, the search for life beyond our own pale blue dot. For centuries, we have gazed up at the stars and wondered if we are alone, if somewhere out in that vast cosmic ocean, another spark of consciousness is looking back at us. Today, that question is no longer just a philosophical one, it's a scientific pursuit, and we are closer than ever to finding an answer. We have become cosmic explorers, armed with telescopes and technology, scanning the heavens for signs of a living world, and what we are finding is more incredible and diverse than anything we ever dreamed. This video is your invitation to join that grand adventure, a journey to the frontiers of known space to explore the most promising candidates for alien life ever discovered. We are about to embark on a cosmic safari, visiting 30 extraordinary exoplanets, planets orbiting other stars, each with its own unique story and potential. Some of these distant worlds are bathed in perpetual twilight, locked in a gravitational embrace with their star. Others float in the perfect Goldilocks zone, where temperatures are just right for liquid water to pool on the surface. We will wander through hypothetical atmospheres rich with the chemical signatures that could hint at biological processes and dive into the profound mysteries of what life, in all its possible forms, might look like in such alien environments. This isn't just a list, it's a voyage to the cutting edge of astronomy and astrobiology, a guided tour of our best hopes for finding that we are not alone in the universe. So prepare to have your imagination stretched and your sense of wonder rekindled. We are leaving behind everything familiar to explore worlds that challenge our very understanding of what a planet can be. From super-Earths with crushing gravity to watery worlds with global depths, the diversity is staggering. The discoveries we are about to uncover represent the collective work of thousands of scientists and the powerful gaze of our most advanced observatories. They are the pieces of a cosmic puzzle we are only just beginning to assemble. So let's begin this journey together to cross the light years and explore these 30 exoplanets that just might be the place where we finally discover we have neighbors in the cosmos. Our journey begins not in some distant, unfamiliar corner of the galaxy, but right on our cosmic doorstep. Just over 4 light-years away, in the constellation of Centaurus, orbits a world that has captivated astronomers and dreamers alike, Proxima Centauri b. This isn't a far-flung abstraction. This is our next-door neighbor, a planet with a mass strikingly similar to Earth's, nestled in the habitable zone of its star, Proxima Centauri. The mere existence of a potentially rocky world so close to us, in the region where temperatures could allow for liquid water to exist on its surface, is a monumental discovery. It fundamentally changes the question from "are there other Earths?" to "could the very first one we found harbor life?" But the environment of Proxima Centauri b is anything but a simple copy of our own world. Its host star is a red dwarf, a smaller, cooler, and far more tempestuous star than our Sun. This creates a set of extraordinary conditions. Because the star is so faint, its habitable zone is incredibly close in. Proxima Centauri b orbits its Sun in a mere 11 days, a breathtakingly short year that places it 20 times closer to its star than Earth is to the Sun. This intimate dance likely results in a phenomenon called tidal locking, where one hemisphere of the planet permanently faces the star in endless daylight, while the other is plunged into perpetual frozen night. This presents a fascinating puzzle for potential habitability. life would need to find a way to thrive in the twilight ring, the Terminator line, where the scorching day side meets the frigid night side, a narrow band where temperatures might be just right. The challenges don't end there. Red dwarf stars like Proxima Centauri are notorious for their violent outbursts. They frequently unleash massive stellar flares, eruptions of radiation and charged particles that could be hundreds of times more powerful than anything our Sun produces. A planet like Proxima Centauri b, sitting so close, would bear the full brunt of these cosmic storms. Such events could potentially strip away a planetary atmosphere over billions of years, or bathe the surface in levels of ultraviolet and X-ray radiation that would be lethal to life as we know it. The survival of any atmosphere, and therefore any liquid water, hinges on whether the planet possesses a strong protective magnetic field like Earth's to deflect this relentless stellar fury. Yet, for all these daunting challenges, Proxima Centauri b remains one of the most tantalizing targets in the entire search for life. Recent climate models suggest that with a sufficiently thick atmosphere or a global ocean, heat could be transported from the day side to the night side, potentially creating much broader temperate regions than we initially thought. The possibility of a vast, liquid water ocean on its surface cannot be ruled out. This world represents a test case, a laboratory for understanding the extremes of planetary environments. It teaches us that habitability is not a simple yes or no checkbox, but a complex and resilient spectrum. Proxima Centauri b stands as a profound reminder that the first place we look for our cosmic neighbors might be the one closest to home, a world of stark contrasts and breathtaking possibilities. Now, let's journey from our nearest stellar neighbor to a truly unique planetary system that redefines the idea of a solar family. About 40 light-years away, orbiting an ultra-cool red dwarf star, we find the Trappist-1 system and its crown jewel, Trappist-1e. While Proxima Centauri b introduced us to the concept of a solitary, tidally locked world, Trappist-1e is part of an extraordinary cosmic community, a system of 7 rocky planets, all crammed into a space smaller than Mercury's orbit around our Sun. This incredible proximity means that if you were standing on the surface of Trappist-1e, the other 6 worlds would appear in your sky not as faint points of light, but as magnificent, vivid orbs, some appearing larger than our own moon. You'd have multiple neighboring worlds hanging there, a constant, breathtaking reminder that you are part of a closely knit planetary family. What makes Trappist-1e itself so compelling is its striking similarity to our own world. This isn't a bloated gas giant or a scorching super-Earth. It is almost a perfect twin of Earth in terms of its size, mass, and density. That last point, density, is crucial. It strongly suggests that Trappist-1e is a rocky planet just like Earth, Venus, and Mars. It has the right kind of solid ground beneath its feet, or potentially the right kind of seabed. Even more importantly, it orbits squarely in the middle of its star's habitable zone. This is the region often nicknamed the Goldilocks zone, where the temperature from the star is just right, not too hot and not too cold, for liquid water to potentially exist on the planet's surface. Unlike the extreme tidal locking of Proxima b, some climate models suggest that Trappist-1e could even have a temperate, Earth-like climate with a regular day-night cycle, potentially allowing for a more familiar environment where life could take root and flourish. The existence of its 6 siblings creates a dynamic environment unlike anything in our own solar system. These worlds are gravitationally dancing incredibly close to one another. Their tight orbits mean that they exert small but persistent gravitational tugs on each other, a process known as tidal heating. This internal friction could generate enough warmth inside these planets to keep their geologic engines running, potentially powering volcanic activity and sustaining subsurface oceans even if their surfaces are frozen. This opens up a fascinating possibility. While Trappist-1e might have a clement surface, one of its siblings could be a frozen world with a vast, warm ocean hidden beneath a thick crust of ice, much like Jupiter's moon Europa. In such a scenario, the Trappist-1 system wouldn't just host one life-bearing world, but could become a network of habitable environments, a celestial archipelago where the seeds of life might even travel between planets on fragments of rock blasted into space by asteroid impact. Yet, the same star that provides the energy for this potential paradise also presents its greatest challenge. The Trappist-1 star is even quieter than Proxima Centauri, but it is still a red dwarf subject to flaring, especially in its youth. The key question is whether Trappist-1e and its siblings were able to hold onto their atmospheres through the star's volatile early phases. Current observations are actively seeking to answer this, looking for the chemical fingerprints of an atmosphere when the planets pass in front of their star. The discovery of a thick, protective atmosphere around Trappist-1e would be a game-changer, transforming it from a promising candidate into arguably the most important world in the search for alien life. It represents the hope that around the most common type of star in our galaxy, life has found a way to not just survive, but to thrive in a system of stunning complexity and beauty. Leaving the tightly packed family of Trappist-1, we venture next to a world that marked a true turning point in our cosmic search. Over 500 light-years away, in the constellation Cygnus, orbits Kepler-186f. Before its discovery in 2014, we had found many planets in habitable zones, but they were almost all significantly larger than Earth, so-called super-Earths or mini-Neptunes. Kepler-186f was different. It was the very first planet we ever discovered that was nearly identical in size to our own world and was confirmed to be orbiting comfortably within its star's habitable zone. This was the moment the search for another Earth moved from theoretical possibility to tangible reality. It was no longer a question of if we could find an Earth-sized world in the right place, but how many were out there. This pioneering world circles a star that is smaller and cooler than our Sun, a red dwarf much like the hosts of Proxima b and the Trappist-1 planets. Its orbit is much tighter than Earth's, completing a full trip around its star in just about 130 days. Yet, because the star emits less energy, that close orbit still places it in that precious temperate band where liquid water could pool on its surface. What truly sets Kepler-186f apart in terms of its environment, however, is the quality of its light. Imagine standing on its surface and looking up at the local sun. The star would appear with an orange-red hue, and the noon sky would likely be dimmer and redder than our own, more like our experience of a perpetual evening twilight here on Earth. This unique lighting has fascinating implications for the possibility of life, specifically for photosynthesis. Plants on Earth have evolved to use the broad spectrum of our yellow sun, but if life were to arise on Kepler-186f, it might evolve to capitalize on the red and infrared light that dominates its world. This opens up a captivating thought experiment. The landscape could, in theory, be colored in deep shades of black or purple, as pigments that absorb these longer wavelengths would be far more efficient for energy collection. We are forced to expand our imagination beyond a simple green and blue Earth twin and consider a planet that is truly alien in its appearance, yet just as vibrant and alive in its own way. Kepler-186f challenged us to think not just about Earth clones, but about the myriad ways a living world could manifest itself. The discovery of Kepler-186f sent shockwaves through the field of astrobiology. It provided the first concrete evidence that planets with the basic ingredients for life, rocky terrain, a temperate climate, and the potential for liquid water were not one in a million anomalies. They were a common feature of our galaxy. This single finding dramatically increased the statistical probability that life could exist elsewhere. It told us that the universe was not only capable of building worlds of our size and type, but that it was doing so with a frequency we could finally begin to measure. Kepler 186f became a powerful symbol, a beacon proving that our own world is not a cosmic fluke, but rather one of many potential harbors for life in the vast ocean of stars. While the crowded dance of the Trappist system and the pioneering twilight of Kepler 186f open our minds to different kinds of planetary families, our next destination offers something just as precious: stability. About 49 light-years away, nestled in the constellation Cetus, lies a super-Earth named LHS 1140b. This world stands out not for its kinship to others, but for the remarkable tranquility of its home. It orbits a red dwarf star, yes, but this particular star is one of the quietest and most stable we have ever discovered. While its cousins like Proxima Centauri are prone to violent, atmosphere-stripping tantrums, the star LHS 1140 is a calm, mature cosmic citizen, offering its planet a far more gentle and consistent light. This peaceful environment makes LHS 1140b one of the most promising and intensely studied targets in our entire search for life beyond Earth. What exactly is a super-Earth? The term can be a little misleading, as it doesn't necessarily mean the planet is more habitable than our own, or even that it's Earth-like at all. It simply refers to a class of planets with a mass greater than Earth's, but substantially less than that of an ice giant like Uranus or Neptune. LHS 1140b sits firmly in this category, with a mass about 6 times that of our world and a diameter roughly 1.7 times larger. The critical piece of information, however, comes from its density. By measuring both its mass and size, astronomers have been able to calculate that LHS 1140b is incredibly dense. This high density is the key piece of evidence pointing toward a predominantly rocky composition, a world with a solid surface, potentially iron-rich core, and most intriguingly, the possibility of vast amounts of water. Many scientists now suspect that LHS 1140b could be what's known as a mega-Earth, a massive rocky planet, or even a water world completely enveloped by a deep global ocean hundreds of miles deep. Crucially, this substantial world orbits squarely within its star's habitable zone. Its year is a rapid 25 days, but because the star is so faint and cool, this close orbit still places it in that temperate region where water could exist as a liquid. The combination of a rocky composition, the right location, and a stable stellar environment is what elevates LHS 1140b from being just another exoplanet to a top-tier candidate for life. Its calm star means that any atmosphere it formed in its youth was likely not eroded away by billions of years of intense stellar winds and radiation. This gives a potential biosphere a much stronger chance to develop and persist, creating a stable environment over geological timescales, something we believe was essential for the evolution of complex life on our own planet. This unique set of favorable conditions is precisely why LHS 1140b has become a primary target for the most powerful space telescope ever built, the James Webb Space Telescope. The star's quiet nature is a gift to astronomers. When a planet transits or passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths of this light, leaving behind a unique chemical fingerprint. A calm star provides a steady, unwavering background light source, making these incredibly subtle fingerprints vastly easier to detect and interpret against a clean signal. The James Webb Telescope, with its unparalleled infrared sensitivity, is perfectly equipped to analyze this light for signs of key molecules like water vapor, carbon dioxide, and most tantalizingly, potential biosignatures such as methane and oxygen in combination. The ongoing study of LHS 1140b represents a new era in exoplanet science. we are moving beyond simply finding planets to deeply characterizing their environments. With every observation from Webb, we are gathering clues that will help us answer the profound questions about this distant world. Does it have a thick, crushing atmosphere like Venus, or a more temperate, nitrogen-rich one like Earth? Is its surface a global, water-covered abyss, or does it host rocky continents? The answers will not only tell us about LHS 1140b itself, but will also refine our understanding of how common habitable conditions truly are around the galaxy's most abundant stars. This super-Earth, with its quiet sun and promising location, offers us one of our clearest and most stable windows into the potential for life on a world not so different, yet profoundly grander than our own. As we continue our journey, moving from one red dwarf system to another, we encounter a world that stands out for its profound sense of quiet promise. Orbiting a star just 11 light-years away, Ross 128b presents a scenario that feels almost serene compared to the stellar tempests we've witnessed elsewhere. This exoplanet, with a mass very similar to Earth's, circles its host in a remarkably close orbit, completing a full revolution in just under 10 days. Yet, because its star is so much cooler and dimmer than our Sun, that incredibly tight orbit still places it squarely within the habitable zone. The key to its immense potential, however, lies not just in its location, but in the uniquely gentle nature of the star it calls home. The primary challenge for life on most red dwarf planets is the star itself. These stars are notoriously volatile, especially in their youth, frequently erupting with colossal flares that blast their orbiting planets with intense ultraviolet and X-ray radiation. Such stellar activity can systematically strip away a planet's atmosphere over billions of years, leaving behind a barren, irradiated rock. But Ross 128 is different. It's what astronomers classify as an inactive flake star, one of the quietest red dwarfs known in our cosmic neighborhood. It has settled into a stable, mature phase of its life, exhibiting very few of the violent outbursts that plague stars like Proxima Centauri. This tranquility gives Ross 128b a monumental advantage in the race for habitability, the precious gift of a stable environment. With a calm star, the likelihood that Ross 128b has managed to retain a substantial atmosphere over its long history increases dramatically. An atmosphere acts as both a climate regulator and a protective shield, two ingredients considered essential for life as we understand it. Coupled with its Earth-like mass, which strongly suggests a rocky composition, the presence of an atmosphere could allow for liquid water to pool and persist on its surface. This combination, a rocky world in the temperate zone of a peaceful star, makes Ross 128b one of the most compelling candidates for potentially habitable conditions we have yet discovered. It offers a vision of a world that may have enjoyed the consistent, gentle warmth needed for the complex chemistry of life to begin and evolve, free from the constant threat of atmospheric erosion. The environment on Ross 128b would still be profoundly alien. Given its close orbit, the planet is almost certainly tidally locked, meaning one side is locked in permanent daylight while the other is shrouded in endless night. Yet, with a thick enough atmosphere, winds could circulate heat from the hot day side to the cold night side, potentially creating a wide, temperate band along the twilight terminator where conditions might be surprisingly clement. Imagine a landscape where the sun appears as a large, dim, reddish orb hanging motionless in the sky, casting a perpetual, deep sunset glow. Life here wouldn't experience the rhythmic cycle of days and seasons we know, but could find a stable, if unusual, niche in which to thrive. What makes the story of Ross 128 be so powerful is the contrast it provides. It teaches us that not all red dwarf systems are created equal. While many may be hostile environments, others, blessed with calmer stellar parents, could be quiet oases of habitability. This single world forces us to refine our search, to look not just for planets in the right place, but for planets with the right kind of star. Its discovery tells us that serene, life-friendly neighborhoods likely exist throughout our galaxy, and that some of our closest cosmic neighbors might be living in just such a peaceful and promising environment. Moving inward, deep within the 12 light-year distance to the Tegodon star system, we find a world that embodies the quiet, ancient potential for life. Tegodon star B isn't just another rocky planet. It holds the distinction of having one of the highest Earth Similarity Index scores ever calculated, a metric that compares a world's properties to our own and suggests it could be one of the most Earth-like exoplanets known. This planet, with a mass almost identical to Earth's, orbits a star that is profoundly ancient and remarkably stable. Tegodon star is an ultra-cool red dwarf, so faint and calm that it wasn't even discovered until the year 2003, despite being one of our closest stellar neighbors. Its extreme age, estimated to be at least 8 billion years old, means this planetary system has had more than twice the time our solar system has existed to cook the complex chemistry of life. The environment around such a dim star is naturally very different from our sun-drenched world. Tegodon star B completes an orbit in just 4.9 Earth days, an incredibly short year that places it extremely close to its stellar host. Yet, because the star emits only a tiny fraction of our sun's energy, this tight orbit is precisely what lands it in the middle of the habitable zone. The sunlight that reaches this world would be a dim, deep red, and the noonday sky would likely be a perpetual, murky twilight. A critical question for any tidally locked planet like this one is whether heat can be distributed from the permanent day side to the frigid night side. For Tegodon star B, many scientists suspect the answer lies in the potential for a thick, substantial atmosphere. A dense atmosphere would be a game-changer for this world's habitability. Acting like a massive, planet-wide blanket, it could effectively trap the star's feeble heat and circulate it around the globe. This greenhouse effect could prevent the night side from freezing solid and moderate the temperatures on the scorching day side, potentially creating vast swaths of the surface where conditions are temperate and stable. With a thick enough atmosphere, entire oceans of liquid water could exist on Tegodon star B, hidden under a hazy, red sky. The sheer age of the system works in its favor here. Over billions of years, the planet's interior would have had ample time to cool, likely reducing rampant volcanic outgassing that could lead to a runaway greenhouse effect like Venus, allowing a more balanced and life-sustaining climate to develop and persist. This combination of factors, an Earth mass world, a prime orbital position, an ancient quiet star, and the strong possibility of a heat-retaining atmosphere makes Tegodon star B a silent giant in the field of astrobiology. It represents a different kind of hope, not for a world that looks like Earth, but for one that has achieved a stable, potentially habitable state through a completely different evolutionary path. It suggests that some of the most promising cradles for life may not be the bright, youthful systems, but the old, quiet ones that have spent eons in peaceful existence, offering a stable environment where life could have arisen in the deep, distant past and endured in a slow, steady rhythm under the gentle glow of an ancient sun. Venturing further into the cosmic catalogue of the Kepler Space Telescope, we encounter a world that stands as a testament to stellar moderation and planetary promise. Lying over 1,200 light-years away in the constellation Lyra, Kepler 442b represents a class of planets that fills astronomers with a particular kind of excitement, the super-Earth. With a radius about 1.3 times that of our own world, it is substantial enough to potentially hold onto a thick, life-sustaining atmosphere, yet not so massive that its gravity would crush all hope for a complex biosphere. But what truly sets Kepler 442b apart, and what has earned it a place among the most Earth-like worlds ever identified, is its exquisite placement in what scientists call the conservative habitable zone. This distinction is crucial. The habitable zone is often thought of as a broad band where liquid water could exist. However, the conservative habitable zone is a much more refined concept. It's the sweet spot within the sweet spot, the region where a planet is not only far enough from its star to avoid a runaway greenhouse effect, but also close enough to prevent a global, irreversible freeze. Kepler 442b doesn't just skirt the edges of this zone, it resides comfortably within its heart. This optimal positioning suggests a world that has a much stronger chance of maintaining stable, temperate conditions over geological timescales, a key ingredient for the slow, patient evolution of life. The star it orbits plays a pivotal role in this promising scenario. Unlike the red dwarfs we've visited so far, Kepler 442b's host is a K-type star, often referred to as an orange dwarf. These stars are a wonderful middle ground between our intense yellow sun and the faint, tempestuous red dwarfs. They are more stable and long-lived than sun-like stars, with lifespans that can stretch for tens of billions of years, offering any emerging life an extraordinarily long, stable window to evolve. Even more importantly, the amount of light Kepler 442b receives from its orange sun is calculated to be about 70% of what Earth gets from our sun. This is a remarkable figure. It means the energy bathing this distant world is not so weak that photosynthesis would be a struggle, nor is it so intense that it would readily scorch a planetary surface. This opens up a profound possibility that is far less certain around dim red dwarfs: the potential for oxygen-producing photosynthesis. On Earth, this process is the bedrock of our entire planetary biosphere. The sunlight levels on Kepler 442b appear to be more than sufficient to power a similar biological engine. Imagine a landscape where plants, or whatever life forms fulfill that ecological role, bask under an orange-hued sun. They might develop pigments optimized for the specific light spectrum of their star, potentially coloring their world in shades of deep red or violet instead of our familiar green. The very fact that we can so plausibly envision a thriving, photosynthesizing ecosystem on a world over 1,000 light-years away is a staggering testament to its Earth-like qualities. Of course, significant questions remain. Being a super-Earth, its surface gravity would be stronger than what we experience. Walking on this world would feel heavier, a constant reminder of the planet's greater mass. The composition of its atmosphere is still unknown. It could be a thick, crushing blanket of gases or a more temperate, nitrogen-rich envelope like our own. Yet, when astronomers run the numbers on metrics like the Earth Similarity Index, Kepler 442b consistently scores among the highest of all the thousands of exoplanets discovered by Kepler. It may not be a perfect twin of our world, but it presents a compelling vision of a planet that has won the cosmic lottery. A stable orbit in the most clement part of the habitable zone, bathed in a gentle and nurturing sunlight, and offering an environment where the fundamental processes that sparked life on our own planet could not only be possible, but could thrive under an alien orange sky. Just a stone's throw away in cosmic terms, a mere 14 light-years from Earth, we find a planetary system that offers a dramatic lesson in fine margins and gravitational interplay. Orbiting the red dwarf star Wolf 1061 is a world that sits precariously on the edge of possibility, Wolf 1061c. This super-Earth, with a mass at least 4 times that of our own planet, holds the distinction of being one of the closest potentially habitable exoplanets ever discovered. Its existence so near to us ignites our imagination, but a closer look reveals a world living on a knife's edge, a testament to how a planet's specific address within the habitable zone can make the difference between a watery oasis and a scorching hellscape. What makes Wolf 1061c so fascinating and so cautionary is its precise orbital position. It doesn't orbit in the comfortable middle of its star's habitable zone. Instead, it skirts the inner edge closer to its sun. This placement subjects the planet to significantly more stellar energy than a world like Earth receives. In such a position, the risk of a runaway greenhouse effect becomes a central question. This is the terrifying process we believe transformed Venus from a potentially watery world into the scorching, acidic inferno it is today. It begins when a planet's oceans start to evaporate due to increasing heat. Water vapor is itself a potent greenhouse gas, so more vapor in the atmosphere traps more heat, which in turn evaporates more oceans, creating a vicious, unstoppable cycle that can ultimately boil a world dry and leave it with a crushing, toxic atmosphere. Wolf 1061c, by virtue of its close-in orbit, is flirting with this very fate. Yet, this super-Earth story is not written solely by its distance from its star. Wolf 1061c is part of a dynamic, tightly wound trio of planets, a mini-solar system where gravitational forces are constantly at play. Its orbit is not a perfect, steady circle. It's slightly eccentric, meaning it follows a more elliptical path. This irregularity is likely caused by the persistent gravitational tugs from its two sibling planets, one orbiting closer to the star and one orbiting further out. This constant pulling and nudging introduces a fascinating variable into the climate equation. Orbital eccentricity can lead to significant seasonal temperature swings. If the planet's atmosphere is just right, these seasons could actually help prevent a permanent global boil by creating a cycle of heating and cooling. However, if its atmosphere is already too thick, the added heat at its closest approach to the star could be the final push needed to trigger that irreversible greenhouse catastrophe. The potential environments on Wolf 1061c are thus a study in extremes. If it managed to hold onto a substantial amount of water and possesses an atmosphere more like Earth's, it could be a tropical, water-rich world with global oceans and a steamy, thick haze. Life there would have evolved to withstand intense heat and humidity. Conversely, if it succumbed to the greenhouse effect, its surface would be a scorching wasteland, utterly inhospitable, a stark reminder that simply being in the habitable zone is not enough. A third, equally compelling possibility is that it exists as a tidally locked eyeball planet. With one hemisphere permanently facing the star, a vast, scorching desert would dominate the dayside. On the night side, a permanent frozen wilderness would reign. But right at the terminator line, the boundary between light and dark, a narrow ring of potentially temperate conditions could exist. Here, a single giant ocean might persist, shaped like a giant eyeball staring out into space, a fragile oasis clinging to existence in a world of extremes. Ultimately, Wolf 1061c serves as a crucial case study. It teaches us that habitability is not a simple, static label but a delicate and dynamic balance. Its story is one of tension between the heat of its star and the composition of its atmosphere, between the stability of its orbit and the gravitational influence of its planetary neighbors. This nearby world forces us to ask difficult questions and refine our search. As we look out at the galaxy's countless red dwarf systems, we must remember that many potentially habitable worlds may be living on this same precarious edge, their fates hanging in the balance of forces seen and unseen. Now prepare to visit a world that challenges our most basic assumptions about what a solar system should look like. Just 22 light-years away, in the constellation of Scorpius, we find the remarkable exoplanet GJ667cc. This super-Earth doesn't just orbit a single star, it is part of a complex triple-star system, a celestial ballet that would provide an utterly breathtaking sky. The planet itself orbits a small, cool red dwarf star known as GJ667c. But if you were standing on its surface, you would look up to see not one, but two additional suns hanging in the heavens. A pair of orange dwarfs that dance around each other in the distance, appearing in the sky as two brilliantly luminous orbs far brighter than our full moon. This isn't science fiction, this is the stunning reality of a world in a stellar family of three. Despite this seemingly chaotic arrangement, GJ 667cc exists in a pocket of surprising stability, nestled firmly within its primary star's habitable zone. Its year is a swift 28 days, but the most astonishing figure is the amount of energy it receives. Astronomers calculate that this planet absorbs almost exactly the same amount of stellar energy from its dim red sun as Earth does from our own. This is a critical piece of the puzzle. It means that, thermodynamically speaking, the potential for liquid water on a rocky surface is just as strong here as it is on our own world. This perfect energy balance, achieved in a system with 3 stars, tells us that the cosmic recipes for habitable environments are far more varied and resilient than we ever imagined. The planet's composition adds to its intrigue. With a mass at least 3.5 times that of Earth, GJ 667cc is classified as a super-Earth. Detailed studies of its properties strongly suggest it is a rocky world, much like our own, but with a more substantial and massive frame. This greater mass comes with both challenges and advantages. The surface gravity would be significantly stronger, making every movement more laborious and potentially shaping life forms to be stockier and closer to the ground. However, this strong gravity also offers a major benefit. It would be exceptionally good at holding onto a planetary atmosphere. Over billions of years, a thick atmosphere is a precious shield against stellar radiation and a vital blanket for maintaining stable surface temperatures. This potential atmosphere is where the story of GJ 667cc becomes truly fascinating. The star it primarily orbits, GJ 667c, has a chemical composition that is notably different from our Sun. It is what astronomers call metal poor, meaning it contains a lower abundance of elements heavier than hydrogen and helium. This is significant because planets form from the same cloud of material as their star. A metal-poor star might be expected to host planets that are also lacking in rocky, Earth-like materials. Yet, GJ 667cc exists, a clear rocky world in a system that theoretically shouldn't have been rich enough in heavy elements to form it. This paradox suggests that the planet could have a very distinct geological and atmospheric composition, potentially rich in different ratios of elements than we find on Earth. Imagine the implications for life in such an environment. The very building blocks, the chemistry of the soil, the oceans, and the air could be fundamentally different. This opens up the incredible possibility of a biosphere that operates on a different chemical foundation than our own. Life on Earth is carbon-based and relies heavily on elements like oxygen, nitrogen, and phosphorus. On GJ 667cc, with its potentially unique elemental abundances, biology might have found alternative pathways. Perhaps it utilizes different elements in its metabolic processes or constructs its cellular structures from novel compounds. The existence of this world forces us to broaden our definition of life's requirements, considering that it might not need an exact replica of Earth's chemistry to flourish. The sky itself would be a constant, dazzling spectacle. The 2 other stars in the system would shine with a warm, orange glow, providing a significant amount of additional light, especially during their daytime when they are above the horizon. While they are too far away to provide substantial heat, their light would be more than enough to read by at night, casting complex, shifting shadows across the landscape. The concept of true darkness might be rare on this world, a place illuminated by multiple suns. The seasonal and daily cycles would be incredibly complex, governed by the orbital periods of all 3 stars. Life here would evolve under a canopy of perpetual, multi-source light, which could drive the development of sensory systems and biological rhythms unlike anything we know. GJ 667cc stands as a powerful symbol of cosmic diversity, proving that stable, life-friendly conditions can arise even in the most complex and seemingly improbable stellar environments. Our journey now takes us over 1,000 light-years from Earth to a star system that harbors one of the most intriguing ocean world candidates ever found, Kepler-62f. This remarkable planet, slightly larger than our own at about 1.4 times Earth's radius, completes a leisurely orbit around a star considerably smaller and cooler than our Sun. Its year is not a matter of days or weeks, but a full 267 Earth days. This extended orbit places it squarely on the outer reaches of its star's habitable zone, a location that creates a fascinating set of possibilities for what kind of world this might be. Unlike planets like Wolf 1061c that skirt the inner edge and risk overheating, Kepler-62f faces the opposite challenge, the potential for a deep global chill. Because it receives a relatively modest amount of stellar energy comparable to what Mars gets from our Sun, the surface temperatures on Kepler-62f would likely be far colder than what we experience on Earth. Without a significant atmosphere to trap heat, its surface could be a global, frozen wasteland. But this is where the planet's other qualities come into play. Its size and mass strongly indicate a rocky composition, a world with a solid surface, and being a super-Earth, it has the gravitational pull necessary to hold onto a substantial atmosphere. This combination is the key to unlocking its true potential. A thick atmosphere, rich in greenhouse gases like carbon dioxide, could act as a planetary blanket, raising surface temperatures through a powerful greenhouse effect well above what the meager sunlight alone could provide. This opens the door to one of the most captivating scenarios in all of exoplanet science, the possibility that Kepler-62f is a vast water world, a panthalassic planet completely shrouded by a single global ocean. With a thick atmosphere keeping temperatures above freezing, the entire surface could be liquid water, an abyss with no land in sight stretching from pole to pole. The oceans could be dozens or even hundreds of miles deep, with pressures at the bottom so immense that water would form exotic states of ice, not from cold, but from sheer compression, creating a solid seafloor of hot ice. In such an environment, life would be entirely aquatic, potentially thriving around hydrothermal vents on that strange, icy seabed, in an ecosystem completely divorced from sunlight. Alternatively, Kepler-62f could present a world of starkly contrasting environments, an eyeball planet taken to its ultimate expression. If its atmosphere is just thick enough to prevent a total freeze but not sufficient to warm the entire globe, we might find a world locked in a dynamic equilibrium. The side of the planet permanently facing its star, if it is tidally locked, could host a single, giant, liquid water ocean, a circular sea of open water hundreds of miles across. This liquid pupil would be surrounded by a vast iris of glacial ice that gradually thickens as you move into the permanent twilight and then the eternal night of the far side. This would create a planet with one temperate, open ocean, while the rest of the world is encased in a crust of ice, a truly alien geography where all liquid water is concentrated in one immense star-facing basin. What makes Kepler-62f so compelling is that it represents a different kind of habitable template. It's not a potential Earth twin basking in warmth, but a world whose life-giving potential is almost entirely governed by the composition and thickness of its air. It teaches us that the outer boundaries of habitable zones are not necessarily barren frontiers, but could be hiding some of the most spectacular oceanic real estate in the galaxy. This distant, cool world challenges us to think beyond our own parochial experience of climate and consider the profound role a planet's atmosphere plays in transforming a cold rock into a potential harbor for life, a hidden aquatic jewel orbiting a faint sun. Now we arrive at a world that, perhaps more than any other, has earned the title of Earth's older, larger cousin. 1,200 light-years away in the constellation Cygnus, the discovery of Kepler-452b sent a ripple of excitement through the scientific community and the public imagination alike. What sets this planet apart is not just its own properties, but the remarkable familiarity of its home star. Kepler 452 is a G-type yellow dwarf star, virtually a twin of our own Sun in terms of size, temperature, and brightness. It is approximately the same age as our Sun, around 6 billion years old, and has settled into the same stable, middle-aged phase of its life. For the first time, we found a planet of this potential class orbiting a star that truly looks like home, bathing its world in a type of light and a quality of energy that we intrinsically understand. This Earth-like star hosts a planet in an orbit that feels almost uncannily familiar. Kepler 452b circles its Sun in 385 days, a year just 20 days longer than our own. More importantly, its orbital distance places it firmly in the middle of its star's habitable zone, receiving only about 10% more stellar energy than Earth does from the Sun. This combination, a Sun-like star and an Earth-like orbit, is the closest architectural match to our own solar system we have yet found around another star. It creates a powerful and compelling scenario, a world that has been enjoying stable, Sun-like conditions for billions of years, offering a potentially colossal timescale for the slow, patient processes of planetary evolution and just possibly the emergence of life. However, the cousin label is key, signaling both similarity and important difference. Kepler 452b is a super-Earth with a diameter about 60% larger than our planet. This size difference has profound implications. Its mass and surface gravity would be significantly stronger, likely more than twice what we experience. Walking on this world would be a strenuous effort, a constant heavy pull. This increased gravity would also profoundly shape the planet's geology and atmosphere. It could lead to a much more dramatic and active volcanic landscape, as the planet's massive interior retains heat for longer and drives more vigorous tectonic activity. Think of a world with mountain ranges that tower over our Himalayas and volcanic plains that dwarf anything on Earth. This very geological activity, however, could be one of the keys to its long-term habitability. A planet with active plate tectonics and volcanism is able to recycle carbon and other elements through its crust and atmosphere, creating a natural thermostat that can regulate the climate over geological timescales. This process, known as the carbonate-silicate cycle, is believed to be crucial for maintaining the stable temperatures that allowed life to flourish on Earth for so long. On Kepler 452b, with its greater internal heat, this planetary regulatory system could be even more robust and long-lasting. The planet's older age means it has had an extra 1.5 billion years for its geological and biological systems to develop and mature under that stable, Sun-like glow. Imagine a biosphere that has been evolving for 1 billion years longer than life on Earth. The sheer expanse of time opens up staggering possibilities for complexity and adaptation. The flora under a sun nearly identical to our own might appear vaguely familiar in color, optimized for the same light spectrum, but the forms could be utterly alien, shaped by the high gravity into low, sprawling, and incredibly sturdy structures. Animal life, should it exist, would also be built to withstand the relentless pull, potentially with thick, powerful limbs and robust skeletal frameworks. The atmosphere itself is a great unknown. It could be a thicker, denser version of our own, which would help scatter the sunlight and create brilliant, permanent red-orange sunsets across the sky. Or if the planet experienced a runaway greenhouse effect in its distant past, it could be a scorching, Venus-like hellscape. The current evidence, however, points toward a rocky world that has likely held onto its water and atmosphere, making it one of our most powerful and poignant symbols of a potentially living world that is not just a fleeting possibility, but a long-enduring reality. Kepler 452b offers us a vision of what our own planet might become in its far future, a mature, massive world teeming with ancient life, orbiting a star that has shone steadily for eons. While we often focus our search on rocky super-Earths, a truly groundbreaking discovery has forced us to completely rethink where life could exist. orbiting a red dwarf star about 120 light-years away. K2-18b is not a terrestrial planet like Earth. It's a mini Neptune, a class of world significantly larger than our own, with a radius more than twice that of Earth and a mass nearly 8 times greater. For years, we assumed such planets were simply smaller, gassier versions of Neptune, with no solid surface, just layers of crushing hot gas and perhaps a small, rocky core at the center, making them utterly inhospitable. But K2-18b, nestled within its star's habitable zone, has completely upended that assumption, revealing a new and thrilling category of potentially life-bearing world. The paradigm shift occurred when astronomers, using the Hubble Space Telescope, detected the unmistakable spectral signature of water vapor in the planet's atmosphere. This was monumental. It marked the first time water vapor had ever been identified in the atmosphere of a habitable zone planet outside our solar system. But the composition of that atmosphere is what truly redefines the possibilities. Unlike Earth's nitrogen-oxygen envelope, K2-18b is believed to be shrouded in a thick, extensive atmosphere dominated by hydrogen, with a significant amount of water vapor present. This specific combination, a hydrogen-rich atmosphere over a vast, hot ocean, is the very definition of a hypothetical environment scientists have dubbed a Hycean world. The concept of a Hycean world is both alien and awe-inspiring. Picture a planet with no continents, no shorelines, and no land of any kind. Instead, the entire surface is a single global ocean, so deep it could span hundreds or even thousands of miles. This water would not be cool and refreshing. Under the thick atmospheric blanket, the surface of this ocean could be hot, perhaps reaching temperatures close to the boiling point of water on Earth. Yet, because of the immense pressure from the overlying atmosphere and ocean, the water remains in a liquid state. Above this global sea, the sky would not be blue. It would likely be a perpetual, deep haze of hydrogen and water clouds, creating a permanent, pressurized, and steamy environment unlike anything we can truly imagine. It is within this seemingly hostile global ocean that the potential for life emerges. The hydrogen-rich atmosphere, while toxic to complex life as we know it, could serve as a powerful greenhouse blanket, trapping just enough heat from its faint red dwarf star to maintain those vast liquid oceans. But the real magic might happen not at the scorching surface, but deep below in the ocean's abyssal layers. As you descend, the pressure increases dramatically, and the temperature, counterintuitively, could drop to more clement levels. Life on Earth thrives around hydrothermal vents at the bottom of our own oceans, completely independent of sunlight, drawing energy from the planet's internal heat and chemical reactions. In the dark, deep waters of a Hycean world, a similar ecosystem could exist, flourishing around geologic hotspots on the ocean floor, completely shielded from the alien sky above. The discovery of K2-18b and its water vapor has fundamentally expanded the playing field in the search for life. It tells us we should not limit our search to planets that look like Earth. Entire classes of worlds we once wrote off as hopeless gas balls could, in fact, be the most common abodes for life in the universe. The next crucial step is to use the James Webb Space Telescope to probe the atmosphere of K2-18b in even greater detail. Astronomers will be hunting for more than just water. They will be looking for the telltale biosignature gases that could hint at biological activity, such as dimethyl sulfide, a molecule produced in vast quantities by marine phytoplankton on Earth. Finding such a chemical in the hydrogen-rich air of this distant world would be a discovery of staggering proportions, suggesting that life can not only arise in a global, boiling ocean, but can become pervasive enough to change the very chemistry of its planet's sky. Our next destination takes us to a world that has become a benchmark for atmospheric mystery, a super-Earth that has stubbornly guarded its secrets for years. Just 48 light-years away in the constellation Ophiuchus, GJ 1214b orbits a small red dwarf star, and it was one of the first of its kind to have its atmosphere directly studied. What we found, or more accurately, what we didn't find, has fueled a captivating and ongoing scientific debate. This planet is larger and more massive than Earth, but smaller than Neptune, placing it squarely in a category that is frustratingly ambiguous. Is it a water world, a globe-spanning ocean planet with a steamy, dense atmosphere? Or is it something else entirely, a mini-Neptune with a small, rocky core drowned under a vast, deep envelope of hydrogen and helium gas? The answer has profound implications, as one scenario could point toward a potential habitat, while the other suggests a crushingly hostile environment. The key to this mystery lies in the planet's atmosphere, and the primary tool for investigating it is a technique called transmission spectroscopy. When GJ 1214b passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmospheric fringe. Different gases in this airless shell absorb specific wavelengths of this light. By carefully analyzing which colors are dimmed more than others, astronomers can piece together the atmosphere's chemical composition. The initial observations of GJ 1214b yielded a startling result. The planet's atmosphere showed a completely flat spectrum. No specific chemical fingerprints, like those of hydrogen or water vapor, were clearly visible. It was as if a uniform, opaque curtain was hanging over the entire planet, blocking our view of the layers beneath. This puzzling flat line pointed toward two very compelling, yet very different explanations. The first possibility is that GJ 1214b is shrouded in a thick, global layer of high-altitude clouds or a pervasive photochemical haze. Think of it as a planetary-scale version of the smog that sometimes blankets large cities, but on a far grander and more impenetrable scale. These wouldn't be fluffy water clouds like we have on Earth, but likely clouds composed of other compounds such as zinc sulfide or potassium chloride exotic salts that can condense high in the atmosphere of a hot world. This dense, unbroken cloud deck would effectively scatter the starlight uniformly, creating that featureless spectrum and hiding the true nature of the atmosphere below from our telescopes. The second, and even more thrilling, possibility is that GJ 1214b is not shrouded in clouds at all, but is in fact a massive water world with a steamy, water-rich atmosphere. In this scenario, the planet could be composed of a staggering 50% or more water by mass. Imagine a world with a rocky core, but instead of having separate oceans and continents, the entire planet is enveloped by an ocean thousands of miles deep. The atmosphere above this global sea would be incredibly dense and humid, dominated by water vapor. Under the intense heat from its close orbiting star, where surface temperatures could soar to hundreds of degrees Fahrenheit, this water would be in a supercritical state, a strange, fluid-like gas that could also produce a relatively flat transmission spectrum. The high pressure at the ocean's surface would create exotic forms of ice like Ice 7, a hot, solid state of water that forms under immense pressure, effectively creating a solid seafloor. Distinguishing between these two models, a cloudy mini-Neptune or a steamy water world, is one of the great challenges in modern exoplanetology. The internal structure of the planet holds some clues. If it has a low density, it suggests a large, puffy atmosphere of light gases like hydrogen, supporting the mini-Neptune model. If its density is higher, it points toward a composition richer in heavier materials like water and rock, favoring the water world hypothesis. Current measurements lean toward a fairly high density, giving significant weight to the ocean planet idea. However, the evidence is not yet conclusive. This ongoing debate highlights a critical truth about exoplanet science. Planets that fall between Earth and Neptune in size represent a completely new class of world, one without any direct analog in our own solar system. GJ1214b is the prototype for these enigmatic sub-Neptunes, and understanding its true nature is key to unlocking the secrets of the thousands of similar planets we have since discovered. It stands as a testament to the fact that some of the most intriguing discoveries are not clear answers, but profound and motivating mysteries. Our journey now takes us to a system that was once thought to be a simple family of hot, rocky worlds, until a closer look revealed a hidden gem with a far more temperate address. 42 light-years away in the constellation Pictor, the star HD 40307 was initially known to host 3 super-Earths, all orbiting so close to their sun that their surfaces would be scorching wastelands. But then, advanced data analysis techniques uncovered a 6th planet in the system, a discovery that completely reshaped our understanding of this cosmic neighborhood. This world, designated HD 40307g, was found to be orbiting at a much more comfortable distance, placing it squarely within the star's habitable zone and instantly transforming it into one of the most exciting candidates for a life-friendly environment we had identified in the early days of exoplanet hunting. What makes this super-Earth particularly compelling is the nature of its host star. HD 40307 is a K-type orange dwarf, a category of star we've come to appreciate as a potential sweet spot for habitability. These stars are more stable and longer-lived than our own sun, offering a steady, dependable source of energy for billions of years longer than G-type stars can provide. For a planet like HD 40307g, which is estimated to be about 7 times the mass of Earth, this stellar stability is a gift. It means the planet has likely been bathed in a consistent and gentle flow of warmth for eons, providing the kind of long-term climatic stability that could allow for the slow, gradual evolution of prebiotic chemistry and perhaps life itself. Perhaps the single most important feature of HD 40307g, and one that sets it apart from many of the tidally locked worlds orbiting red dwarfs, is its potential for a regular day-night cycle. The planet's orbit is far enough from its star that it may very well rotate on its own axis, just like Earth, Mars, and Venus do in our solar system. This simple fact has profound implications. A rotating planet avoids the extreme environmental dichotomy of tidal locking, where one hemisphere is baked in permanent daylight and the other is frozen in eternal night. Instead, HD 40307g could experience a natural cycle of days and nights, with the star's heat and light being distributed more evenly across the globe. This would prevent any one side from becoming a scorching desert or a deep frozen ice sheet, creating a much wider range of potentially temperate environments. Imagine the landscapes this could produce. With a surface gravity roughly twice that of Earth's, walking would be a heavy, laborious endeavor, and any life forms would likely be built low to the ground to withstand the constant pull. Yet, under an orange-tinted sun, this massive world could boast a diverse and dramatic geography. The higher gravity would allow for the potential of a much thicker atmosphere, which could lead to spectacular weather patterns with immense cloud formations and powerful winds racing across the sky. Vast oceans could cover significant portions of the surface, their waves moving with a slower, more ponderous rhythm under the strong gravitational field. Mountain ranges might tower higher than anything on Earth, their peaks piercing through a dense, hazy sky. The discovery of HD 40307g was a landmark moment in exoplanet science because it was one of the very first potentially habitable super-Earths found around a sun-like star. It helped to shatter the early assumption that most planetary systems would be compact and hostile, proving instead that stars could host multiple planets with a wide variety of orbital distances, including some in that precious temperate band. This world taught us to look more carefully at known systems, to reanalyze the data with fresh eyes, because a habitable oasis might be hiding in plain sight. a previously overlooked member of a planetary family once written off as entirely uninhabitable. It stands as a testament to the power of scientific curiosity and refinement, a world that emerged from the shadows of data to offer a compelling vision of a massive, rotating planet enjoying a stable and enduring spring under the light of a mature and gentle star. Now, let's turn our attention to a system that has long captivated science fiction writers and astronomers alike, a star that is practically in our backyard and visible to the naked eye. Just under 12 light-years away, the Sun-like star Tau Ceti has been a beacon in our night sky for millennia, and we now know it hosts its own family of planets. Among them, the super-Earth Tau Ceti e demands our focus. This is a substantial world with a mass at least 4 times that of Earth, and it occupies a profoundly intriguing yet precarious position in its solar system. It doesn't orbit in the comfortable middle of the habitable zone. Instead, it skims the inner edge, a placement that makes its story a gripping tale of 2 possible futures, hinging almost entirely on the nature of its atmosphere. Because it orbits so close to its star, completing a year in just 168 days, Tau Ceti e receives a significant amount of stellar energy, substantially more than Earth does from the Sun. This intimate proximity subjects the planet to an intense and constant barrage of heat. In such a position, the planet's fate is a delicate balancing act. If Tau Ceti e possesses only a thin or moderate atmosphere, the surface could be scorchingly hot, likely far too warm for liquid water to exist in a stable state. It would be a barren, sun-baked world, more akin to a super-Venus than a super-Earth. However, the more compelling and perhaps more likely scenario involves a very different kind of environment, one sculpted by the planet's substantial gravity. As a massive super-Earth, Tau Ceti e would have the powerful gravitational pull necessary to capture and hold onto an incredibly dense, thick atmosphere. This is where the potential for a runaway greenhouse effect becomes the central theme of its story. Imagine an atmosphere dozens of times thicker than our own, dominated by gases like carbon dioxide and water vapor, both of which are potent greenhouse gases. Such a dense shroud would act as an extraordinarily efficient planetary blanket, trapping the immense heat from its star with devastating effectiveness. The surface temperatures could soar to hundreds of degrees, hot enough to melt lead and boil away any oceans that might have once existed. In this case, Tau Ceti e would be a permanent global pressure cooker, a hellish landscape with crushing atmospheric pressure and searing heat, a stark warning of how a planet's location and mass can conspire to create an uninhabitable inferno. Yet, there is a fascinating alternative lurking within this greenhouse narrative. If the atmospheric composition were just right, not overwhelmingly thick, but sufficiently dense, it could theoretically create a very different, albeit still extreme, environment. Some climate models suggest the possibility of a superhabitable state where the thick atmosphere effectively distributes heat, preventing the dark side of the planet from freezing if it is tidally locked, and creating vast regions with stable, albeit very warm, temperatures. The entire planet could be shrouded in a permanent layer of highly reflective clouds, which might bounce a considerable amount of stellar energy back into space, helping to moderate the extreme heat. In this speculative scenario, life would have to be an extremophile, thriving in hot, high-pressure conditions, perhaps in a global steam bath-like environment or in deep, shadowed oceanic trenches. Adding a dramatic layer of complexity to this story is the Tau Ceti system itself, which is far from a serene and orderly place. Observations have revealed that Tau Ceti is surrounded by a massive and dense debris disk, a vast belt of comets, asteroids, and dust that contains far more material than the similar disk in our own solar system. This tells us that the planetary system is dynamically active, a place where collisions and bombardments are likely common events. For a planet like Tau Ceti e, this presents a dual-edged sword. On one hand, a frequent barrage of cometary impacts in the system's early history, could have been the delivery mechanism for the very water and organic compounds that are the building blocks of life, seeding the planet with the ingredients for a biosphere. On the other hand, an ongoing high rate of large impacts would pose an existential threat to any established life, potentially causing regular extinction-level events that would reset the evolutionary clock. The presence of this massive debris disk paints a picture of a system that is either a fertile nursery for life's ingredients or a chaotic shooting gallery, and possibly both at different times in its long history. Tau Ceti E, therefore, stands as a world of profound contrasts and high stakes, a massive planet in a familiar star system whose true nature is a tense standoff between the stifling grip of a greenhouse atmosphere and the chaotic legacy of a violent cosmic neighborhood. Sometimes the most profound discoveries are not made by looking out, but by looking back. Hidden within the vast archives of data collected by the Kepler Space Telescope, a world of immense promise was waiting patiently to be found. After the telescope's primary mission had ended, a team of scientists and citizen scientists combed through old observations, and their diligence revealed a gem that had been initially missed by automated algorithms. This world is Kepler 1649c, a planet that instantly captured our imagination because of one stunning, simple fact. It is one of the most Earth-sized and Earth-like worlds we have ever discovered beyond our solar system, a near twin in terms of raw physical dimensions. Located about 300 light-years away, this rocky planet orbits a faint red dwarf star. Its size is its most immediately striking feature, with a radius estimated to be just 1.06 times that of Earth. It is virtually identical to our own world in sheer physical scale. This is a critical distinction from the many super-Earths we've encountered. Kepler 1649c isn't a larger, more massive cousin. It is a direct sibling in size, strongly suggesting a similar rocky composition and a gravity that would feel very familiar to us. Finding a planet of such a precise terrestrial scale in the habitable zone is a relatively rare event, making this rediscovery all the more significant. But a planet's size is only part of the story. Its location is everything, and Kepler 1649c occupies a truly prime piece of cosmic real estate. It orbits squarely within its star's conservative habitable zone, that sweet spot where liquid water could theoretically exist on the planetary surface. Even more compelling is the calculation of its stellar energy intake. Astronomers have determined that the amount of light Kepler 1649c receives from its small, cool sun is about 75% of the energy Earth gets from our sun. This places it in a remarkably similar, if slightly cooler, energetic environment. In terms of the balance of heat and light, this world is far more comparable to Earth than many other celebrated candidates, orbiting in a temperate band that seems perfectly poised for climate stability. This combination of an Earth-like size and an Earth-like energy budget is what elevates Kepler 1649c to its status as one of Kepler's greatest legacies. When scientists compute its Earth Similarity Index, a metric that compares a planet's properties to our own, it scores remarkably high, ranking among the top exoplanets ever found by the mission in its resemblance to our home world. It presents a scenario that is both comforting and electrifying. A rocky planet, almost exactly our size, basking in a level of sunlight not too different from what illuminates our own polar regions, offering an environment where the chemistry of life as we know it could plausibly operate. Of course, this promising picture comes with the caveats common to worlds around red dwarfs. Its orbit is incredibly tight, with a year lasting just 19.5 Earth days, and it is almost certainly tidally locked to its star. This means one side is a permanent landscape of daylight, while the other is trapped in an endless, deep frozen night. The potential for habitability then hinges on the same fascinating dynamics we've seen elsewhere, the presence of a substantial atmosphere. A thick enough atmospheric envelope could circulate heat from the scorching day side to the frigid night side, potentially carving out a vast, temperate ring along the twilight terminator where conditions are just right for liquid water to pool and persist. The discovery of Kepler 1649c is a powerful reminder that our own data holds hidden treasures, and that an almost perfect analog to our own world was waiting quietly in the numbers, a testament to the enduring power of human curiosity and the promise that Earth may not be a unique masterpiece, but one of a common and wonderful kind. But what of a world that was never meant for life? Shifting our gaze from the warm embrace of the habitable zone, we turn to a much colder and more distant member of the Proxima Centauri family, Proxima Centauri c. This enigmatic super-Earth is a study in contrast to its famous sibling. While Proxima b is a rocky world tucked in close, enduring the star's fiery temperament, Proxima c is a massive planet orbiting far out in the frozen depths of the system. Its existence tells a different kind of story, one of a planetary system's surprising complexity and the unexpected places where life might find a way to cling to existence. Proxima Centauri c is a substantial world with a mass estimated to be at least 7 times that of Earth. It carves out a wide, lonely path around its dim red sun, taking approximately 5.5 Earth years to complete a single ponderous orbit. This places it about 1.5 times farther from its star than Earth is from our Sun, a distance that sounds deceptively close until you remember the nature of its host. Proxima Centauri is so faint that at this orbital distance, Proxima c receives virtually no meaningful stellar warmth. Its surface temperature, if it has one, is likely a bone-chilling negative 230 degrees Celsius, cold enough to freeze air solid. This is not a world bathed in light, but one shrouded in perpetual, deep space gloom, a frozen giant in a silent, dark orbit. With such a distant and frigid orbit, the surface of Proxima Centauri c itself is almost certainly a sterile wasteland. If it possesses a surface, it would be a landscape of rock and ice under a black sky, with the tiny, faint red dot of Proxima Centauri providing little more than a bright starlight in the darkness. The planet's substantial mass means it could have accreted a thick atmosphere, but at these temperatures, that atmosphere would likely be frozen onto the surface, a layer of solid nitrogen, methane, and other gases creating a bizarre, icy crust. The primary scientific interest in this planet lies not in its own habitability, but in the tantalizing possibility that it could be a miniature solar system in its own right, playing host to a family of moons. This is where the narrative turns from a tale of a frozen world to a thrilling speculative frontier. A massive super-Earth like Proxima c, with its strong gravity, is a prime candidate for possessing a system of large, substantial moons. And it is on these hypothetical moons that the story of life in this system could take a dramatic and unexpected turn. While the feeble light of Proxima Centauri provides no warmth, another powerful force could be at work: tidal heating. Just as Jupiter's gravity squeezes and stretches its moon Io, making it the most volcanically active body in our solar system, the gravitational pull of massive Proxima c could flex and heat its moons from the inside out. Imagine one of these moons, a frozen sphere of rock and ice, similar to Jupiter's Europa or Saturn's Enceladus. On its surface, the environment is lethally cold and dark. But deep beneath that icy crust, the constant gravitational kneading from Proxima c could generate enough internal heat to maintain a vast, global liquid water ocean. This hidden sea, sealed away from the frigid vacuum above by a thick, protective shell of ice, could be a warm, dark, and watery abyss. On the floor of this subsurface ocean, hydrothermal vents could spew mineral-rich fluids into the water, creating chemical energy gradients, the very kind of environment that many scientists believe may have cradled the first life on Earth, entirely independent of sunlight. The potential for such a hidden ecosystem transforms Proxima Centauri C from a barren ice giant into a potential guardian of a secret subterranean biosphere. Its role is not to host life itself, but to provide the gravitational engine that makes life possible on its orbiting companions. This concept dramatically expands the concept of a habitable zone. It's no longer just a band around a star where surface water can flow. It becomes a property of a planetary system where tidal forces can create liquid water environments in the most unlikely of places, far from the star's warming light. The discovery of Proxima C reminds us that when we search for life, we must look not only at planets but at their satellites, and that a cold, dark world can be the key to unlocking a warm, hidden ocean. Now we turn our attention to a system that showcases the remarkable precision of modern planet hunting. Just over 100 light-years away, in the constellation Dorado, a small, cool red dwarf star named TOI 700 hosts a family of planets, and one of them has become a landmark discovery. TOI 700d is an exoplanet that ticks almost every box on our wish list. It is almost exactly Earth-sized, it orbits squarely within its star's conservative habitable zone, and it is a rocky world in a multi-planet system. What makes its discovery by NASA a test mission so extraordinary is the level of certainty astronomers have been able to achieve. Unlike many early candidates that required years of follow-up observation to confirm, test data, combined with other telescopes, provided a clear and robust detection, making TOI 700d one of the first Earth-sized habitable zone planets discovered by the mission that we can say with high confidence is real. The environment around this quiet M-dwarf star is one of ordered rhythms. TOI 700d is the outermost of 3 known planets in the system, taking a leisurely 37 days to complete its orbit. This places it perfectly within the star's temperate band, receiving about 86% of the stellar energy that Earth gets from the Sun. This energy level is strikingly similar to that of Mars in our own system, but with a crucial difference. TOI 700d is a much larger and more massive world than Mars, giving it the gravitational strength to potentially hold onto a thick, life-sustaining atmosphere. Like many planets orbiting faint stars, it is almost certainly tidally locked, with one hemisphere perpetually bathed in the light of its sun, and the other plunged into an eternal, starless night. This tidal locking creates a dramatic environmental puzzle, but one that a robust atmosphere could solve. Without an atmosphere, the day side of TOI 700d would be scorching, while the night side would be a cryogenically frozen wasteland. However, sophisticated climate models funded by NASA have painted a far more hopeful picture. They suggest that with a dense, Earth-like atmosphere, winds and ocean currents would act as a planetary circulatory system, efficiently transporting heat from the hot day side to the cold night side. This process could prevent the atmosphere from collapsing onto the surface as ice on the dark side, and could create a wide, temperate ring of habitability along the terminator line. In the most optimistic scenarios, this could mean that a significant portion of the planet, perhaps even the entire day side, enjoys moderate temperatures that could support liquid water on the surface. Scientists have explored several compelling models for what TOI 700d might actually be like, and the possibilities are fascinatingly diverse. One scenario envisions the planet as a water world completely shrouded by a global ocean. In this case, the heat redistribution would be incredibly efficient, potentially creating a planet-wide, steamy environment with a thick cloud deck constantly shrouding the star-facing side. Another model suggests a more familiar hybrid world. Imagine a landscape where the central region of the day side is a vast, open ocean acting as a heat reservoir. As you move toward the terminator, this ocean gives way to habitable landmasses, continents basking in the perpetual sunset glow, where the climate is moderated by the constant flow of warm, moist air from the dayside sea. The planet could even be a dry world, but with a carbon dioxide-rich atmosphere that creates a strong enough greenhouse effect to keep the entire globe above freezing, resulting in a mostly arid landscape with liquid water possible only in certain regions. The confirmation of this world by TESS, the Transiting Exoplanet Survey satellite, marks a pivotal moment in astronomy. TESS is designed to survey the entire sky, monitoring the brightest stars for the telltale dips in light that occur when a planet transits. TOI 700D was a perfect catch, a clear, recurring signal from a bright, nearby star. Its discovery demonstrated that TESS was fully capable of finding small, Earth-sized planets in the habitable zones of their stars, planets that are prime targets for the next generation of telescopes. The quiet nature of the TOI 700 star itself is a huge advantage for future study. Unlike more active red dwarfs, it shows no signs of strong flaring, which means any atmosphere around TOI 700D has likely been stable for billions of years, giving life a long, undisturbed window in which to emerge and evolve. This world stands as a testament to our growing expertise in finding not just any planets, but the right kind of planets, setting the stage for the day when we can point our most powerful observatories at its faint light and finally seek the chemical signatures of a living world. Shifting our gaze to a relatively nearby system just 31 light-years away, we encounter a super-Earth that masterfully illustrates how a planet's atmosphere can completely redefine its potential. Orbiting the quiet M-dwarf star GJ 357, the world known as GJ 357d resides in the outer, colder reaches of its star's habitable zone. The raw statistics might initially seem discouraging. This planet receives a similar amount of stellar energy from its faint sun as Mars does from ours. On the surface of Mars, that meager energy results in a frozen, barren desert. But GJ 357d is no Mars. It is a massive super-Earth, at least 6 times the mass of our own planet, and that dramatic difference in scale opens the door to a profoundly different climatic destiny. The sheer mass of GJ 357d is the key to its tantalizing promise. This isn't a small, rocky body with weak gravity. It's a substantial world with the powerful gravitational pull necessary to capture and hold onto a very thick, extensive atmosphere. While Mars's thin wisp of an atmosphere is utterly incapable of retaining heat, a dense global shroud around GJ 357d could act as an immensely effective planetary blanket. This is the greenhouse effect pushed to its most life-affirming extreme. The atmosphere would trap the scant incoming stellar radiation, preventing it from escaping back into space. Through this process, the surface temperature could be raised by hundreds of degrees, potentially creating a temperate environment where liquid water could flow, despite the planet's distant and chilly orbital address. The orbital dynamics of this system further enhance its intrigue. GJ 357d takes about 55 Earth days to complete a revolution around its star, placing it significantly farther out than any planet in our own inner solar system. Yet, because the host star is so small and cool, this orbit still lands it within the calculated habitable zone. Its location on the outer edge means it avoids the perilous risks of a runaway greenhouse effect that threatens inner planets like Wolf 1061c. Instead, its primary challenge is the opposite, avoiding a global, permanent deep freeze. The dense atmosphere it likely possesses is the perfect solution to this challenge, transforming what should be an icy wasteland into a potential haven for life. Imagine the possible environments on such a world. With a thick atmosphere, possibly rich in carbon dioxide or nitrogen, the surface pressure would be immense, many times greater than what we experience on Earth. Walking there would feel like moving through a dense, heavy fluid with a strong gravity adding to the sensation of weight. The sky overhead might not be blue, but rather a perpetual, hazy orange or deep red, with complex cloud layers constantly churning in the effort to distribute heat from the warmer day side to the frigid night side, assuming the planet is tidally locked. The landscape itself could be dominated by a global ocean, its surface kept liquid not by intense sunlight, but by the insulating effect of the planet's own air. Or it could be a world of ice and rock, with vast regions still frozen, but with temperate zones near the equator or along the terminator line where liquid water persists in lakes and rivers. The discovery of GJ 357d, confirmed in data from NASA test satellite, underscores a critical lesson in our search for life: context is everything. A planet that receives a Martian level of insulation is not automatically a dead world. Its physical properties, particularly its mass and its ability to maintain a robust atmosphere, can completely rewrite its climatic story. This super-Earth demonstrates that the habitable zone is not a one-size-fits-all region, but a concept that must be filtered through the unique characteristics of each world. A massive planet on the cold outer fringe, wrapped in a warm, dense atmospheric coat, can be just as promising a candidate for life as a smaller world basking in the comfortable center. It expands our vision of what a living planet can be, proving that warmth can come from within a world's own gaseous envelope, creating an oasis of habitability far from the warmth of its star. Journeying back to the earliest days of the Kepler mission, we encounter a world that served as a beacon of possibility, a proof of concept that ignited a new era in the search for life. Announced in 2011, Kepler 22b holds the distinction of being the very first planet discovered by the Kepler telescope to orbit comfortably within the habitable zone of a Sun-like star. At a distance of over 600 light-years in the constellation Cygnus, this discovery was a monumental milestone. It wasn't just another exoplanet, it was a validation of the mission's core purpose. For the first time, we had concrete evidence that stars like our own Sun could host worlds in that temperate band where liquid water could exist, transforming the search for another Earth from a hopeful dream into a tangible scientific pursuit. The star Kepler 22b calls home is a G-type yellow dwarf, a close cousin to our Sun, though slightly smaller and cooler. This similarity was profoundly significant. After finding so many planets around turbulent red dwarfs, discovering a world in the habitable zone of a stable, Sun-like star felt like coming home. Kepler 22b completes a leisurely 290-day orbit around this star, a year strikingly similar in length to our own. This orbital period places it squarely in the middle of the star's habitable zone, receiving about 25% less stellar flux than Earth. In terms of sheer location and stellar environment, Kepler 22b presented an almost idyllic scenario, a world with the potential for a stable, long-term climate under a familiar yellow sun. However, the planet itself is where the Earth-like comparison begins to diverge. Kepler 22b is not a rocky twin of our world, it is a super-Earth with a radius about twice that of Earth. This size places it in a fascinating and ambiguous category. It is too large to be confidently classified as a rocky planet like Earth, yet potentially too small to be a full-blown gas giant like Neptune. This puts it squarely in the enigmatic class of mini-Neptunes, a type of world not found in our own solar system. A planet of this size could have several different structures. It might possess a relatively small, rocky core surrounded by an immensely deep and massive atmosphere of hydrogen and helium, making it a gaseous world with no solid surface. Alternatively, it could be what scientists call a water world, a planet composed predominantly of water and other ices, with a rocky core at the center but enveloped by a global ocean thousands of miles deep, topped with a thick, steamy atmosphere. This uncertainty about its true nature is the central mystery of Kepler 22b. If it is a mini-Neptune with a thick, hydrogen-rich envelope, the pressure and temperature at the bottom of that atmosphere would be so immense that any potential for life as we know it would be extinguished. There would be no surface to speak of, only a gradual transition from gas to a supercritical fluid, a hot, dense, and utterly alien state of matter. But if it is a water world, the possibilities become far more intriguing. Imagine a planet with no continents, no mountains, and no land whatsoever. The entire surface would be a single global ocean, so deep that the pressure at the seabed would create exotic forms of ice, known as high-pressure ices, forming a solid barrier between the liquid ocean above and the rocky mantle below. In such an environment, life could potentially thrive in the dark, vast waters, far removed from the sunlight, perhaps drawing energy from hydrothermal vents on the ocean floor, much like the ecosystems found in Earth's deepest trenches. The legacy of Kepler 22b, therefore, is not that it was the Earth twin we were hoping for, but that it revealed the stunning diversity of worlds that could exist in habitable zones. It taught us that habitable does not always mean Earth-sized. It forced astronomers to broaden their definition of a life-bearing planet to include entirely new categories like the Hycean worlds we discussed earlier. Kepler 22b was the pioneer that proved the search was viable, that sun-like stars could host planets in the Goldilocks zone, and it opened our eyes to the fact that these planets could be far larger, stranger, and more diverse than we had ever imagined. It stands as a grand, beautiful enigma, a foundational discovery that paved the way for every habitable zone planet found after it, reminding us that the first step into a new frontier often reveals not what we expect, but something that expands our very understanding of what is possible. Venturing just over 36 light-years away to the constellation Vela, we find a world that, for a time, held the title of one of the most promising candidates for habitability we had ever identified. Orbiting the K-type orange dwarf star HD 85512, the super-Earth HD 85512b captured the scientific community's imagination upon its discovery in 2011. What made this planet so compelling was not just its location within the habitable zone, but its specific, precarious address right at the inner edge of that temperate band. This placement makes its story a masterclass in the delicate balances that govern a planet's climate, where the difference between a watery oasis and a scorching Venus-like inferno could come down to a single, beautiful, and commonplace phenomenon: clouds. As a super-Earth with a mass estimated to be at least 3.5 times that of our own planet, HD 85512b has the gravitational muscle to hold onto a substantial atmosphere, a crucial prerequisite for life. It orbits its orange sun in a brisk 54 days, a year that feels incredibly short until you consider the nature of its star. K-type stars are cooler and dimmer than our sun, so their habitable zones are nestled in much closer. This close orbit, however, places HD 85512b in a thermally critical position. It receives just slightly more stellar energy than the upper limit what scientists believe could trigger a runaway greenhouse effect. This is the terrifying tipping point where a planet's oceans begin to boil, filling the atmosphere with water vapor, a powerful greenhouse gas which traps more heat, evaporates more water, and spirals until the world is left a dry, scorched husk. HD 85512b is, in essence, living on the climatic razor's edge. This is where the humble cloud becomes the hero of the story. When scientists first modeled the potential climate of HD 85512b, they found that its fate hinged almost entirely on one variable: albedo, or how much sunlight it reflects back into space. Their models revealed a fascinating and hopeful scenario. If the planet possessed an Earth-like atmosphere and, crucially, at least 50% cloud cover, these clouds would act as a planetary sunshield. By reflecting a significant portion of the incoming stellar radiation, the clouds could effectively cool the planet's surface, preventing temperatures from ever reaching the boiling point of water. This simple, natural thermostat could be all that stands between a temperate, life-friendly world and a permanent global heatstroke. The clouds wouldn't just be weather, they would be the guardians of the planet's entire biosphere. The potential environments on such a world are fascinating to envision. Being so close to its star, HD 85512b is likely tidally locked, with one hemisphere forever facing the daylight and the other locked in eternal night. Yet, with that critical cloud cover and a robust atmosphere, this could create a remarkably stable climate. The permanent day side might be dominated by a vast, warm ocean, its waters constantly evaporating to feed the extensive cloud decks that shield it from the full intensity of the star. These clouds would then be carried by powerful winds toward the terminator line, the border between day and night where they would release their precipitation. This could create a lush, temperate band in the perpetual twilight, a region of rolling mist, frequent rain, and potentially a landscape thriving with life. The night side, while cold, would be insulated by the atmospheric circulation, preventing the entire atmosphere from freezing out. The early identification of HD 85512b as a high-priority target was a watershed moment. It was one of the first handful of planets placed on the habitable exoplanets catalog, a curated list of worlds deemed most likely to host life. Its discovery, alongside others like it, signaled a shift in exoplanet science from pure discovery to preliminary characterization. We were no longer just asking, is there a planet there, but were beginning to ask, what is it like there? HD 85512b taught us to think critically about climate feedbacks and to appreciate that a planet's habitability is not defined by orbit alone, but by a complex interplay of stellar energy, atmospheric composition, and even basic meteorology. It showed us that a world living on the edge could still be a paradise, its climate saved by the very same fluffy, white formations we watch drift across our own sky. Returning to the stunning cosmic archipelago of the Trappist-1 system, we now journey to its more distant and serene outpost, Trappist-1g. This world, the sixth in line from its ultra-cool dwarf star, offers a different kind of promise, one not of balmy surface temperatures, but of hidden internal warmth. While its siblings like Trappist-1e orbit in the comfortable middle of the habitable zone, Trappist-1g resides farther out, in a region where the faint starlight provides little surface heat. It's a larger planet than Earth with about 30% more gravity, and its environment would likely be one of profound cold, with any surface water existing as a global, kilometers-thick shell of ice. Yet, this frozen exterior may be deceiving, hiding what could be one of the most fascinating aquatic environments in the entire galaxy. A vast, global subsurface ocean, kept liquid not by sunlight, but by the relentless, churning energy of tidal forces. The key to this world's potential lies in the very same gravitational dance that makes the Trappist-1 system so unique. All 7 planets are packed into an incredibly tight space, orbiting closer to their star than Mercury does to our Sun. This proximity creates an intricate web of gravitational interactions. As Trappist-1g and its siblings swing around their orbits, they constantly tug on one another, their gravity minutely stretching and squeezing each other's interiors. This process, known as tidal heating, generates immense internal friction. Think of it as the planetary equivalent of repeatedly bending a metal coat hanger. After a while, it becomes warm to the touch. On a planetary scale, this effect can produce far more heat than the planet receives from its faint, distant star. For a world like Trappist-1g, this means that while its surface may be a frozen wasteland, its subterranean depths could be warm, dark, and teeming with liquid water. This concept transforms our image of Trappist-1g from a simple frozen ball to a dynamic, layered world. The planet's substantial size and gravity would help it retain this internal heat, preventing its core from cooling completely. Scientists speculate that beneath a thick, icy crust, perhaps dozens or even hundreds of miles thick, a global ocean could churn, its depths kept from freezing by the constant geothermal energy welling up from the seafloor. This would create an environment startlingly similar to what we believe exists on icy moons in our own solar system, like Jupiter's Europa or Saturn's Enceladus. An abyssal world permanently sealed away from the cosmos above, with no sunlight, no seasons, and no atmosphere to speak of, yet potentially rich with the chemistry needed for life. The sky from the surface of Trappist 1G would be a breathtaking, star-studded spectacle. Its host star would appear as a large, dim, reddish orb, casting a weak twilight glow across the icy plains. But the true marvel would be the view of its planetary neighbors. Several of the other Trappist-1 worlds would appear as sizable, vivid disks in the sky, some larger than our own full moon, their cloud patterns and surface features potentially visible to the naked eye. You would witness these celestial bodies move perceptibly across the heavens over just a few days, a constant, majestic reminder of the intricate gravitational ballet that is actively shaping the environment beneath your feet. This interplay between a serene, frozen surface and a dynamic, heated interior makes Trappist 1G a world of captivating duality. The possibility of life in such a hidden ocean is a thrilling prospect. Without sunlight, any ecosystem would have to be entirely chemosynthetic, drawing energy not from photosynthesis but from chemical reactions. On the seafloor of this dark ocean, hydrothermal vents, like the black smokers found in Earth's deepest trenches, could be spewing mineral-rich, superheated water into the darkness. These vents would create oases of energy capable of supporting complex communities of microorganisms and perhaps even larger, more complex life forms, all thriving in complete isolation from the universe above. The discovery of such life on Trappist 1G would carry a profound implication. That life may be most common not on Earth like surface worlds, but in the warm, dark oceans hidden beneath the ice of countless frozen planets and moons throughout the cosmos. This distant, cold member of the Trappist-1 family teaches us that a world need not look like Earth to be a vibrant harbor for life. Sometimes the most promising biospheres are the ones we cannot see, hidden away in the warm, dark heart of an icy world. Now, let's set our sights on a super-Earth that reminds us just how varied the architectures of solar systems can be. Over 2,500 light-years from Earth, in the constellation Lyra, the planet Kepler 443b presents a scenario quite different from the tight, rapid orbits we've often encountered around red dwarfs. This world, with a mass more than 6 times that of Earth, occupies the outer territories of its star's habitable zone, tracing a wide, patient arc around its orange K-type sun. Its orbital period is a substantial 177 days, a year that feels far more akin to the rhythms of our own inner solar system than the frantic weeks-long cycles of many other habitable zone candidates. This more distant and deliberate orbit carries profound implications for the planet's environment, its potential for life, and the immense challenges we face in trying to study it. The most immediate consequence of this wider orbit is a much lower probability of tidal locking. We've grown accustomed to worlds where one face is permanently scorched by daylight and the other frozen in endless night, a common fate for planets huddled close to their faint red dwarf stars. But Kepler 443b, with its greater orbital distance from a larger, brighter star, experiences a much weaker gravitational gradient. This makes it far more likely that the planet rotates on its own axis, experiencing a regular cycle of days and nights. The absence of tidal locking would be a monumental advantage for global climate stability. Instead of a world of harsh extremes, Kepler 443b could enjoy a more even distribution of stellar energy. Heat and weather patterns would circulate across the globe, preventing any single hemisphere from becoming a scorching desert or a cryogenic ice trap. This opens the possibility for a wider variety of temperate environments, where continents could experience seasons and weather systems could develop in a way that feels more familiar to us, all under the light of an orange-hued sun. However, its address on the outer frontier of the habitable zone comes with its own distinct set of challenges. The star Kepler 443b orbits provide significantly less warmth per square meter than our Sun provides to Earth. To maintain surface temperatures above freezing, this super-Earth would rely heavily on a powerful greenhouse effect. This means its habitability is critically dependent on the composition and thickness of its atmosphere. A dense shroud of greenhouse gases such as carbon dioxide or methane would be essential to trap the limited incoming stellar radiation and keep its surface warm. Without a sufficiently thick atmospheric blanket, Kepler 443b would likely be a frozen snowball, its potential for liquid water locked away beneath a global sheet of ice. This delicate balancing act highlights a fundamental truth. A planet's location is only part of the story. Its atmospheric makeup is the decisive factor that can transform a cold, rocky orb into a potentially living world or condemn it to a permanent deep freeze. This brings us to the greatest hurdle with Kepler 443b, the sheer difficulty of peering into its environment from such an immense distance. At over 2,500 light-years away, the planet is an incredibly faint target. When it transits in front of its star, the dip in brightness is minuscule, and the signal we receive is buried in noise. Probing its atmosphere through transmission spectroscopy, the technique where we analyze the starlight that filters through the planet's air, becomes an extraordinary challenge. The chemical fingerprints of water vapor, carbon dioxide, or potential biosignature gases like oxygen or methane are incredibly subtle and require a level of precision that pushes our current telescopes to their absolute limits. For a distant world like this, the telltale signs of an atmosphere are often lost in the vast gulf of interstellar space, making conclusive analysis nearly impossible with today's technology. Yet, the very existence of Kepler 443b and others like it in the Kepler dataset is vitally important. It serves as a placeholder for a class of worlds we are only beginning to understand, massive, potentially rocky planets orbiting in the cooler, outer regions of their habitable zones. While we may not be able to characterize its atmosphere today, it remains a prime target for future observatories, telescopes with larger mirrors and more sensitive instruments designed to dissect the faint light from such distant stars. Kepler 443b stands as a promise and a challenge, a reminder that our current map of habitable worlds is still blurry and incomplete, and that some of the most interesting destinations lie in the faint, faraway data, waiting for the next generation of cosmic explorers to bring them into focus. Nestled within the constellation Cygnus, over 800 light-years from Earth, we find a world that embodies the quiet, unassuming hope of finding another pale blue dot. Kepler 1652b may not be a headline-grabbing super-Earth or part of a dazzling multi-star system, but what it lacks in dramatic flair it makes up for in its elegant, Earth-like simplicity. This planet is a testament to the idea that sometimes the most promising candidates for life are not the giant, attention-getting worlds, but the smaller, rocky ones that closely mirror our own home in fundamental ways. With a radius measured at just 1.11 times that of Earth, Kepler 1652b is one of the closest matches to our own world's physical size we have ever discovered. This near-identical scale strongly suggests a predominantly rocky composition, a world with a solid surface, potential continents, and the kind of geological foundation we believe is essential for a stable, long-term biosphere. What truly elevates this world, however, is its exquisite orbital placement. Kepler 1652b doesn't linger on the precarious inner or outer fringes of its star's habitable zone. It resides squarely in the middle of this temperate band, orbiting its red dwarf host once every 2.38 Earth days. This central address is the planetary equivalent of prime real estate. It receives a level of stellar energy that is strikingly well balanced, calculated to be very close to the amount of solar radiation that Earth absorbs from our Sun. This perfect positioning dramatically increases the probability that surface temperatures could be moderate enough for liquid water to exist, provided the planet has one crucial life-giving feature, an atmosphere. And that is the central mystery and the great challenge of Kepler 1652b. Like all planets orbiting red dwarf stars, it faces the existential threat of stellar volatility. During its youth, its star would have been far more active, unleashing powerful flares and a relentless stellar wind that could have scoured away any primordial atmosphere, leaving behind a barren, irradiated rock. The planet's relatively small size and mass work against it here, as it has less gravitational strength to hold onto its gaseous envelope against such an assault. The pivotal question for this world is whether it was able to form with a sufficiently dense atmosphere from the start, or if it possesses a protective magnetic field generated by a churning molten core, a planetary shield that could deflect the worst of the stellar onslaught and preserve its life-sustaining blanket of air. If Kepler 1652b has successfully held onto a substantial atmosphere, the environment on its surface could be remarkably stable, especially considering it is almost certainly tidally locked. With one hemisphere permanently facing its sun and the other locked in endless night, a dense atmosphere would become a global climate regulator. Powerful winds would circulate, carrying heat and moisture from the warm day side to the cold night side. This process could prevent the atmosphere from collapsing as ice on the dark side and could create a vast, temperate ring of habitability along the terminator line, the border between eternal day and eternal night. In this perpetual twilight zone, conditions might be ideal for liquid water to pool in lakes and rivers, creating a narrow but stable band where life could take root and flourish, sheltered from the more extreme temperatures of the planet's two starkly different faces. The story of Kepler 1652b is a powerful reminder that in the search for life, size and location are only the beginning of the story. It represents a class of worlds that are the most direct analogues to Earth we can currently find, rocky, temperate, and of a familiar scale. Yet, its ultimate fate is a lesson in planetary resilience, a demonstration that the ability to nurture life depends on a world's capacity to protect its own delicate environment against the harsh realities of its cosmic neighborhood. This small, distant world holds a quiet significance, a promise that planets built to a similar blueprint as our own are out there, and that their potential for life hinges on the delicate, invisible shield of an atmosphere we are only just learning to detect across the vast expanses of space. Sometimes the most thrilling discoveries are the ones that sneak up on us, not with a grand announcement, but with a quiet, undeniable presence that forces us to sit up and take notice. That is precisely the story of LP 899c, a super-Earth that has rapidly ascended the ranks to become one of the most promising and talked about targets in the entire search for alien life. Discovered just recently orbiting a small, cool red dwarf star located about 100 light-years away in the constellation of Eridanus, this world didn't just join the list, it made a case for being right at the very top. What makes it so special is a rare and powerful combination of factors that align almost perfectly for our current observational capabilities, placing it in the crosshairs of the most powerful space telescope ever built. First, let's consider its physical nature. LP 899c is a super-Earth with a radius roughly 40% larger than our own planet and a mass estimated to be at least 2.5 times greater. This size is a critical sweet spot. It's substantial enough that its gravity is strong enough to hold onto a thick, life-sustaining atmosphere for billions of years. Yet it is not so large that it would have accreted a massive, crushing envelope of hydrogen and helium gas, turning it into an uninhabitable mini-Neptune. All available data strongly points to a rocky composition, a world with a solid surface, potentially dramatic topography, and the right kind of foundation for oceans and continents to form. It is, in essence, a planet built on a grander, more massive scale than Earth, but following the same fundamental blueprint for a terrestrial world. But a rocky composition is only one piece of the puzzle. The true magic of LP 899c lies in its orbit. This super-Earth is the second planet discovered in its system, orbiting farther out from its star than its inner sibling. It takes a leisurely 8.46 Earth days to complete a single year, a rapid journey that places it squarely in the middle of its star's habitable zone. Now, the star itself, LP 899, is an ultra-cool red dwarf, even more petite and faint than the star of the Trappist 1 system. This faintness is actually its greatest gift to the planet. Because the star is so dim, its habitable zone is pulled in very close, but it is also exceptionally stable and well-defined. LP 899 is a remarkably quiet star, showing very little of the violent flaring activity that plagues many other red dwarfs and threatens to strip away the atmospheres of their orbiting planets. This stellar tranquility gives LP 899c a monumental advantage, the gift of a stable, gentle stellar environment where any atmosphere it formed in its youth could have persisted unscathed for eons. This perfect storm of favorable conditions, a rocky super-Earth in the temperate heart of a quiet star's habitable zone, is what has catapulted LP 899c into the scientific spotlight. However, its status as a prime candidate was truly cemented by the way it was discovered and what that means for our ability to study it. The planet was detected using the transit method, meaning it passes directly in front of its host star from our point of view here on Earth, causing a predictable, periodic dip in the star's brightness. This geometric alignment is a golden ticket for astronomers. When a planet transits, a tiny fraction of the star's light filters through the planet's atmosphere. As this light passes through this gaseous envelope, different molecules within the atmosphere absorb specific colors or wavelengths of the light. By meticulously analyzing which colors are missing, we can decode the atmosphere's chemical composition, looking for the fingerprints of water vapor, carbon dioxide, methane, and even potential biosignatures like oxygen. This is where LP 899c truly shines. Among all the known potentially habitable terrestrial planets, it provides one of the most pronounced and cleanest transit signals. Its star is small and dim, so the relative dip in light when the planet passes in front is significant and easy to measure. Even more importantly, because the star is so inactive and quiet, its light is a steady, unwavering beacon. There is no stellar noise from flares or star spots to muddy the delicate signal of the planet's atmosphere. This creates a pristine laboratory for atmospheric characterization. It is as if the universe has handed us a perfectly still pond, allowing us to see the reflection of this alien world's air with stunning clarity. It is for all these reasons that LP 899c has been flagged as one of the highest priority targets for the James Webb Space Telescope. Webb's unparalleled infrared sensitivity is perfectly suited to probe the atmosphere of this distant world. Its instruments can hunt for the spectral signatures of key molecules, and the clarity of the signal from LP 899c means that Webb could potentially detect an atmosphere with just a few transits of observation. The first results could tell us if this super-Earth is shrouded in a thick, Venus-like hellscape of carbon dioxide, a more temperate, nitrogen-rich envelope like our own, or perhaps something even more exotic. The detection of water vapor would be a monumental finding, confirming that this world not has the right temperature, but also one of the key ingredients for life as we know it. LP 899c represents a new era in exoplanet science, where we are moving beyond mere discovery and into the age of deep characterization, probing the very air of another world to answer the ancient question of whether we are alone. But what happens when one of the most promising discoveries in the search for life is a world whose very existence is shrouded in scientific controversy? This brings us to the captivating and enigmatic story of Gliese 581g, a planet that, for a brief, electrifying moment, promised to be the first truly Earth-like world we had ever found beyond our solar system. Orbiting the red dwarf star Gliese 581, located just over 20 light-years away in the constellation Libra, this proposed super-Earth was announced to the world in September 2010. Its estimated mass suggested a rocky world just 3 to 4 times the size of our own, but its most staggering property was its location. It appeared to orbit squarely in the middle of its star's habitable zone. The Discovery team, led by astronomer Stephen Vogt, was so confident in their analysis that they gave the planet an unofficial, deeply personal name, Zarmina's World, after Vogt's wife. For a moment, it felt as if we had reached the holy grail of exoplanet hunting. The initial detection was made using the radial velocity method, a technique that does not see the planet directly, but instead watches for the subtle wobble a planet's gravity induces in its host star. As the star is tugged back and forth by an orbiting world, its light spectrum shifts minutely, blue shifting as it moves toward us and red shifting as it moves away. The team's analysis of years of data from the HIAS instrument in Hawaii indicated not one, but 2 new planets in the system, Gliese 581f, a cold outer world, and the crown jewel, Gliese 581g. The data suggested this world was tidally locked, with one side in permanent daylight and the other in endless night, but with a potential average surface temperature that could allow for liquid water in the temperate twilight zone between the 2 extremes. The announcement sparked a media frenzy and captured the public's imagination like no exoplanet had before. Here was a world that could plausibly have streams, oceans, and maybe even life right in our cosmic backyard. However, the initial euphoria was almost immediately met with intense scientific skepticism. Another prominent team, using a different and extensive dataset from the HARP spectrograph in Chile, reanalyzed the stellar wobbles and could not confirm the signal of Gliese 581g. They argued that the perceived wobble attributed to the planet could be a misinterpretation, perhaps a subtle artifact of the star's own activity and rotation masquerading as a planetary signature. The star Gliese 581 is known to be magnetically active, with starspots and flares that can complicate the delicate measurements of the radial velocity method. The central controversy boiled down to a battle of data and statistical interpretation. Was the signal a genuine planet, or was it noise being mistakenly sculpted into a discovery by the analysis techniques? This division launched a years-long debate in the astronomical community, with some researchers publishing papers supporting the planet's existence and others refuting it, leaving Gliese 581g in a state of scientific limbo, neither fully confirmed nor entirely disproven. Despite the cloud of uncertainty, the potential of Gliese 581g had a profound and lasting impact on the field of astrobiology. It forced scientists to confront, in a very public way, the immense technical challenges involved in finding small, rocky worlds. The controversy highlighted the limitations of the radial velocity method, especially when pushing it to the very edge of its sensitivity to detect Earth-mass planets. It underscored the need for multiple, independent lines of evidence and the importance of data from different instruments to validate such a monumental claim. The debate over Zarmina's World became a cautionary tale and a rallying cry, driving home the point that extraordinary discoveries require extraordinary evidence. It pushed the entire community to refine its methods, improve its statistical models, and demand more rigorous standards for announcing potentially habitable planets. The story of Gliese 581g is more than just a historical footnote about a planet that might not be there. It represents a pivotal moment of transition in our quest. It was the moment the public truly grasped that the search for another Earth was real and imminent. It was the moment scientists were humbled by the sheer difficulty of the task. And it was the moment that set the stage for the more robust multi-mission approach we use today, where telescopes like Kepler and TESS find planets through the transit method, and powerful instruments like HARPS and HIRES work in tandem to confirm them. Even if Gliese 581G ultimately fades from the catalogues, its legacy is secure. It taught us to dream bigger, to question more deeply, and to persevere in the face of ambiguity, because the ultimate prize, a living world orbiting another star, is worth every moment of the struggle. Now, let's turn our gaze toward a world that teaches us a powerful lesson about planetary kinship and the subtle ways that sibling worlds can shape each other's destiny. About 1,500 light-years away in the constellation Lyra, the star Kepler 283 shines as the center of a compact family of planets. It's here we find Kepler 283c, a fascinating exoplanet that, on paper, appears to have won the cosmic lottery. It's remarkably Earth-like in size, with a radius just over 1.5 times that of our own planet, placing it firmly in the category of a rocky super-Earth. Even more importantly, it resides comfortably within its star's habitable zone, orbiting that cooler, fainter sun once every 93 days. This places it in a temperate region where the energy from its star could theoretically allow for liquid water to persist on its surface. At first glance, this seems like the profile of another perfect candidate for life, a world with the right size and the right location. But the story becomes infinitely more interesting when we consider that Kepler 283c does not live in this system alone. Its constant companion is its inner sibling, Kepler 283b, a smaller planet that races around the star in a blisteringly fast orbit of just 11 days. This close-in world, likely a scorching, rocky ball basking in intense stellar radiation, plays a surprisingly pivotal role in the narrative of its outer, more temperate sister. In our own solar system, the planets are spaced widely apart, their gravitational influences on one another relatively gentle and long-term. But in the Kepler 283 system, the two worlds are cosmic neighbors in a much tighter configuration. This proximity means their gravitational fields are in constant, intimate conversation. Every time Kepler 283c completes an orbit, it feels the persistent, rhythmic tug of its inner sibling. This gravitational dialogue does more than just slightly alter orbital paths. It can fundamentally influence the very warmth and geological activity of a planet in profound ways. This phenomenon, known as tidal heating, is a game-changer for a world's potential habitability. Just as the Moon's gravity pulls on Earth's oceans to create the tides, the gravitational force from Kepler 283b continually squeezes and flexes the interior of Kepler 283c. This internal friction generates heat, acting as a secondary engine deep within the planet. This is crucial because a planet's internal heat is the power source for geology. It drives the churning of a molten core, which can generate a protective magnetic field to shield the surface from harmful stellar radiation. It fuels plate tectonics, the planetary scale recycling process that helps regulate a world's climate by moving carbon in and out of the atmosphere over millions of years. For Kepler 283c, this extra internal warmth from its sibling could mean the difference between a geologically dead, frozen world and a vibrant, active one with the right conditions for life to emerge and persist. Yet, this celestial partnership is a delicate balancing act. Too much tidal heating can be just as catastrophic as too little. If the gravitational interactions are too strong, the resulting geologic violence could be overwhelming. Imagine a world with constant, planet-wide volcanic eruptions, a surface continuously resurfaced by flowing lava, and an atmosphere choked with volcanic ash and gases. Such an environment would be far too unstable for the delicate chemistry of life to ever gain a foothold. The situation for Kepler 283c hinges on the precise orbital dynamics between the two planets, the eccentricity of their orbits, and their exact orbital resonance. If their dance is just right, the tidal heating could provide a steady, gentle warmth, perfect for sustaining a stable, life-friendly environment. If their dance is a chaotic jostle, it could churn the planet's interior into a relentless inferno. This introduces a captivating layer of complexity to our search for life. We can no longer judge a planet's habitability on its size and orbit alone. We must now ask, what are its neighbors like? The presence of a planetary sibling, especially one in a close, resonant orbit, can be a hidden variable that either makes or breaks a world's potential. Kepler 283c stands as a brilliant example of this interconnected reality. It suggests that the most promising cradles for life might not be solitary worlds, but planets that exist within a supportive gravitational network, where the gentle, warming embrace of a sibling planet provides the internal fire needed to power the engines of a living world. Its story beautifully illustrates that in the cosmos, as in life, our relationships with those closest to us can fundamentally shape who we become. As our cosmic tour continues, we find ourselves drawn to a star so brilliant and close that it bridges the gap between our solar system and the distant realm of exoplanets. Just 21 light-years away in the constellation Cassiopeia, the star HD 219134 burns brightly, a K-type orange dwarf visible to the naked eye from dark locations here on Earth. Orbiting this beacon is a complex family of at least 6 known planets, and it is the outermost discovered member of this clan, HD 219134G, that captures our imagination. This super-Earth, with a mass over 5 times that of our own world, carves out a wide, patient path around its star, a journey that takes it fully into the system's cold, outer habitable zone. Its existence offers a masterclass in how a planet's potential is not defined by its temperature alone, but by the intricate interplay of its composition, its atmosphere, and the unique advantages of the Sun it calls home. The orbital story of HD 219134G is one of stark contrasts within its own family. Its inner siblings are scorching worlds, with one even classified as a lava planet, orbiting so close that their surfaces are likely molten. But HD 219134G is a distant sentinel, taking a methodical 3 years to complete a single orbit around its orange sun. This places it far beyond the torrid inner system, in a region where the stellar energy it receives is minimal, more akin to the dim, cold light that reaches the dwarf planets in the outer reaches of our own solar system. On the surface, this might seem to condemn it to a permanent, deep freeze. However, this is where the planet's substantial mass becomes its greatest asset. As a super-Earth, its powerful gravity gives it the capacity to hold onto a tremendously thick atmosphere. This dense, global shroud could act as a phenomenal insulator, creating a runaway greenhouse effect in reverse, not to boil an ocean away, but to prevent a world from freezing solid. The very air of this planet could be the furnace that keeps it warm, trapping the feeble starlight so effectively that the surface temperature could be raised by hundreds of degrees, creating pockets where liquid water might persist against all odds. Beyond its tantalizing location, we have strong reasons to believe HD 219134G is a rocky world, a true terrestrial giant. Unlike many super-Earths that drift into the ambiguous category of mini-Neptunes, this planet's density, inferred from its mass and radius, points toward a composition rich in rock and metal. Imagine a landscape of immense, towering mountain ranges and deep, vast canyons, all shaped by a surface gravity nearly twice what we experience on Earth. The very geology of this world would be epic in scale, potentially fueled by immense internal heat from radioactive decay. This rocky foundation is the first and most critical requirement for Earth-like habitability, providing the solid ground upon which oceans could pool and the complex chemistry of life could potentially unfold. It transforms the planet from a hypothetical gas ball into a tangible, alien landscape waiting to be explored. But the single most extraordinary feature of HD 219,134G is not on the planet itself, but in the nature of its star. HD 219,134 is a bright, nearby, and stable K-dwarf, and this makes it an astronomer's dream for future study. While the faint, red dwarfs we've visited often host promising planets, their dimness makes detailed atmospheric analysis incredibly challenging, like trying to read a book by a single flickering candle. HD 219,134, by contrast, is a brilliant spotlight. Its proximity and brightness mean it pours a flood of light toward our telescopes, providing a strong, clean signal. When HD 219,134G transits, if its orbit is aligned such that it passes in front of the star from our viewpoint, the event would be a spectacularly clear and measurable dip in that brilliant light. Even more importantly, that same bright starlight would become a powerful analytical tool. As it filters through the planet's atmosphere during a transit, our next-generation telescopes, like the James Webb Space Telescope and its successors, will be able to dissect that light with unparalleled precision, hunting for the chemical fingerprints of water vapor, carbon dioxide, methane, and even potential biosignatures. This positions HD 219,134G as a strategic keystone in the long-term search for life. It is a world that embodies the transition from mere discovery to deep characterization. While it may be a colder, more massive cousin of Earth, its residence in a system anchored by a brilliant, quiet star gives it an observational advantage that many more Earth-like worlds lack. It offers us a realistic and near-term opportunity to practice reading the atmospheric composition of a rocky planet in a habitable zone, even if that zone is on the chilly side. The lessons we learn from studying its air will be directly applicable to the study of more temperate Earth twins in the decades to come. HD 219,134G teaches us that the perfect laboratory for understanding alien climates might not always be the most obvious one. Sometimes the most valuable world is the one that shines not with its own potential for life, but with the brilliant light of its sun, illuminating the path toward answering our most profound cosmic questions. Now, let's direct our attention to a discovery that emerged from the final, precious days of one of history's most productive space telescopes. As the Kepler mission was drawing to a close, its reaction wheels failing and its fuel nearly spent, it made one last deep dive observation into a small patch of sky. Within that final trove of data, scientists later uncovered a world that serves as a perfect capstone to Kepler's legacy, Kepler 1638b. This exoplanet, located about 3,000 light-years away in the constellation Cygnus, is a testament to the mission's enduring power, a jewel found in the twilight of an incredible journey. What makes it so special is not just its own properties, but what it represents in the grand statistical census of our galaxy. A powerful confirmation that planets like our own are not rare exceptions but common cosmic occurrences. Kepler 1638b hits a remarkable sweet spot in planetary characteristics. Its radius is measured to be just 1.2 times that of Earth, placing it firmly in the category of a terrestrial rocky world. This isn't a puffy mini Neptune or a massive super-Earth. It is a direct sibling to our own planet in terms of physical scale. A world of this size almost certainly has a solid surface, with the potential for familiar geological features like mountains, valleys, and, crucially, the basins necessary to hold standing bodies of liquid water. This Earth-like dimension is the first and most critical box to check in the search for a potentially habitable environment, and Kepler 1638b checks it with authority. But a planet's size is only half the equation. Its location is everything, and this is where its story becomes truly compelling. This rocky sibling orbits a star that is a near twin of our own Sun. Kepler 1638 is a G-type yellow dwarf, sharing a similar size, temperature, and stability with the star that warms our world. This stellar similarity cannot be overstated. While red dwarfs are far more common, their violent youth and tendency to tidally lock planets present significant hurdles for life. A sun-like star, by contrast, offers a stable, gentle, and long-lasting source of energy. Kepler 1638b completes an orbit around this sun-like star every 259 days, a year that is strikingly similar in length to our own. More importantly, this orbital period places it comfortably within the star's conservative habitable zone, that Goldilocks region where the temperature is just right for liquid water to potentially exist on the planetary surface. Here we have a world that is not only built like Earth but is also positioned like Earth, orbiting a star like our Sun. It is, in its fundamental architecture, one of the closest overall analogues to our own home world that the Kepler mission ever found. The discovery of Kepler 1638b, along with other late-stage finds like it, provided the final, crucial data points that allowed scientists to perform a truly groundbreaking calculation, estimating just how common such worlds might be in the Milky Way galaxy. The Kepler telescope's primary goal was never to just find individual planets, but to conduct a statistical survey to determine the fraction of stars that host planets of various sizes and orbits. Finding an Earth-sized planet in the habitable zone of a sun-like star was the ultimate jackpot, but these discoveries are challenging. Because of their large orbits, these planets transit infrequently, and their small size means the dip in starlight they cause is incredibly faint. Kepler had to stare at the same stars for years to have a chance of catching these subtle, repeating signals. When astronomers finally crunched the numbers, incorporating Kepler 1638b and its few precious cousins into their models, the result was staggering. They concluded that as many as 20 to 25% of Sun-like stars in our galaxy could host a rocky planet within their habitable zone. Let that number sink in. With hundreds of billions of stars in the Milky Way, a significant fraction of which are G-type stars like our Sun, this implies there could be billions of worlds with basic Earth-like characteristics. Kepler 1638b is not a lonely oddity. It is a single, brilliant data point in a vast sea of statistical probability, a representative of what is likely an enormous population of temperate, rocky worlds scattered across the galactic disk. This profound statistical significance transforms our perspective on the universe. It means that the cosmic ingredients for life, rocky planets with the potential for liquid water orbiting stable stars, are not scarce resources. They are, in fact, a standard feature of stellar systems. The discovery of Kepler 1638b, pulled from the mission's final breaths of data, is a powerful symbol of perseverance and hope. It tells us that our own pale blue dot is almost certainly not unique, but rather one of countless similar worlds adrift in the great cosmic dark, each holding the same quiet potential for oceans, atmospheres, and perhaps on some of them, the faint, emerging glow of life. And now we reach the final stop on our tour of 30 worlds, a destination that brings our journey full circle, back to the profound hope of finding another Earth. Just 16 light-years away, a stone's throw in galactic terms, orbits a planet that perfectly encapsulates the current frontier of exoplanet science, GJ 1002b. Discovered only in 2022, this world is not a massive super-Earth or a hypothetical gas giant. It is, in the most exciting way possible, almost boringly normal. GJ 1002b has a mass almost identical to that of our own planet, making it one of the very few genuine Earth mass worlds ever found residing comfortably within the habitable zone of its star. After exploring giants and water worlds, this discovery feels like a homecoming, a reminder that the ultimate goal, a true Earth twin, is now within our observational reach. The star it calls home is perhaps its greatest attribute. GJ1002 is a red dwarf, but it belongs to a very special class. It is an exceptionally quiet and inactive star. We've discussed the tantrums of stars like Proxima Centauri, whose flares can sterilize nearby planets. GJ1002 presents the opposite scenario as stellar Zen master. It emits very little in the way of ultraviolet or X-ray radiation, and it shows almost no signs of the violent flaring that characterizes so many of its stellar cousins. For a planet like GJ1002b, which orbits incredibly close with a year of just over 10 days, this stellar tranquility is a gift of incalculable value. It means that over the billions of years of its existence, this Earth-mass planet has likely been spared the relentless atmospheric stripping that other red dwarf worlds endure. The probability that it has held onto a substantial atmosphere, that crucial blanket for life, is therefore significantly higher. Imagine the environment on this nearby world. Bathed in the dim, reddish light of its peaceful sun, the planet is likely tidally locked. One hemisphere would be a landscape of permanent, muted daylight, while the other would lie in an endless, star-filled night. Yet, with a thick enough atmosphere, this stark division could be softened. Winds could carry warmth from the dayside across the terminator line, creating a wide, temperate band where conditions are stable and clement. In this perpetual twilight, under a deep red sky, liquid water could pool in lakes or even vast oceans. The very fact that we can so plausibly envision a stable, watery environment on a planet so small and so close fills this discovery with a sense of immediate promise. What truly sets GJ1002b apart, however, and makes it a perfect note to conclude on, is its immense potential for the immediate future. Its proximity and the quiet nature of its star make it an absolute prime target for the next generation of astronomical observation. The stage is now set for a deeper act in this cosmic drama: atmospheric characterization. Powerful instruments like the James Webb Space Telescope and the upcoming extremely large telescopes on the ground are designed to do exactly this kind of work. They will train their gaze on GJ1002b, watching for the moment it transits in front of its star. When that happens, a tiny fraction of the star's light will filter through the planet's atmosphere. By analyzing that filtered light with spectacular precision, these observatories will be able to detect the chemical fingerprints of the gases in that air. The search will be on for water vapor, the fundamental ingredient for life as we know it. They will look for carbon dioxide, a common planetary gas that can help regulate climate. And most tantalizingly, they will hunt for potential biosignatures, combinations of gases that are difficult to explain without the presence of biology. The simultaneous detection of oxygen and methane in its atmosphere, for example, would send shockwaves through the scientific community, as these gases react with each other and need a continuous source like life to coexist in significant quantities. Because the star is so quiet, the light signal will be clean and unambiguous, giving us our clearest ever look at the air of another Earth-sized world. GJ1002b is not just another entry on a list. It is a promise of a revelation waiting to happen, a world poised to transform from a faint blip in our data into a fully characterized planet with a known climate and just maybe the first hints of a biosphere. It represents the thrilling precipice we now stand upon, where the act of discovery is giving way to the profound art of understanding. But discovering a world is only the beginning of the quest. Knowing that a planet resides in the habitable zone is like finding a beautiful, locked box. The true treasure lies in prying it open to see what's inside. This is where the science of astrobiology shifts from astronomy to chemistry, from locating worlds to reading their atmospheres in a grand cosmic forensic investigation. The ultimate goal is to find a biosignature, a chemical clue in a planet's air that could only be plausibly explained by the presence of life. We aren't looking for cities or radio signals. We are hunting for the faintest ghost of a molecule, a silent testament to biological processes happening light years away. The most promising clues we seek are not single gases, but specific, telltale combinations that are difficult to explain through geology alone. On Earth, our atmosphere is a testament to life. It contains 21% oxygen, a highly reactive gas that would quickly vanish from our air if it weren't constantly replenished by photosynthesizing plants, algae, and bacteria. Oxygen loves to react with other elements, like iron in rocks or carbon in the air, forming stable compounds like rust and carbon dioxide. Finding large quantities of oxygen in an exoplanet's atmosphere, especially alongside a reducing gas like methane, would be a seismic discovery. Methane is another key biosignature. While it can be produced by volcanic activity on Earth, the vast majority of methane in our air comes from biological sources like wetlands, livestock, and the decay of organic matter. Oxygen and methane should not coexist for long. They rapidly destroy each other. To find them together in significant amounts in a planet's atmosphere would imply a continuous, vigorous source for both, a powerful, albeit not certain, hint of an active, living biosphere. Another compelling and perhaps even more robust biosignature is the combination of nitrous oxide with other gases. Nitrous oxide, often called laughing gas, is produced in large quantities on Earth by microbes in soil and the ocean. While it can be generated in tiny amounts by lightning, a substantial, persistent concentration in a planet's air would be very difficult to attribute to a non-biological process. The most powerful evidence will likely come from detecting a whole suite of gases that are in chemical disequilibrium. A planet's atmosphere, left to its own non-living devices, will naturally settle into a stable, boring chemical balance like the carbon dioxide-dominated atmospheres of Venus and Mars. An atmosphere that is far from this equilibrium, buzzing with reactive gases that shouldn't coexist, is an atmosphere that is being actively and perhaps biologically stirred. The technological challenge of this search, however, is almost incomprehensibly difficult. We are trying to detect parts per million traces of gas in the atmosphere of a world that is itself nothing more than a faint speck of dust orbiting a brilliant star millions of times brighter. The primary tool for this is a technique called transmission spectroscopy. When a planet transits passing directly in front of its star from our point of view, a tiny fraction of the star's light, often less than 1%, filters through the planet's thin atmospheric fringe. As this light passes through this gaseous envelope, molecules in the air absorb very specific wavelengths, leaving behind a unique barcode of dark lines in the star's spectrum. Our job is to decode this barcode. For a planet like Trappist 1G or GJ1002b, this signal is incredibly faint. It's like trying to detect the subtle tint added to a massive searchlight after it has passed through a single pane of stained glass from thousands of miles away. This is precisely why telescopes like the James Webb Space Telescope are revolutionary. Webb's powerful infrared eyes are perfectly suited to this task, as many key molecules like water, methane, and carbon dioxide have their strongest absorption features in the infrared part of the spectrum. But even for Webb, this is a Herculean effort. It requires observing multiple consecutive transits of the same planet, carefully stacking the data to amplify the incredibly weak signal from the noise. A single observation is not enough. We need to see the same pattern again and again to be sure we are seeing the planet's atmosphere and not a random fluctuation in the starlight. For the most promising targets like the planets in the TRAPPIST-1 system, astronomers are planning to dedicate hundreds of hours of Webb's precious observing time, all for the chance to glimpse the chemical composition of a world's air. The interpretation of any potential biosignature will also require immense caution. We must be absolutely certain that we are not being fooled by an abiotic false positive. For example, a planet like Venus shows that a runaway greenhouse effect can completely alter a world, and certain geological processes can produce gases we associate with life. A water-rich planet with active volcanism might have an atmosphere rich in carbon dioxide and water vapor, but without any biology at all. This is why context is king. Finding methane on a dry, Mars-like world would be less compelling than finding it on a wet, temperate super-Earth. The final confirmation of life will likely not come from a single observation, but from a preponderance of evidence, a consistent and inexplicable atmospheric cocktail that points toward biology as the only logical conclusion. The hunt for these faint chemical whispers is the next great chapter in our exploration of the cosmos, a meticulous process of elimination that may one day lead us to the ultimate discovery, that we are not alone in the universe. And while our current telescopes are already pushing the boundaries of what's possible, the true revolution in the search for life is just over the horizon, powered by a new generation of observatories being designed right now. Imagine a telescope so powerful it could directly photograph a tiny, pale blue dot orbiting a distant star, separating its faint light from the blinding glare of its sun. This isn't a distant dream, it's the explicit goal of missions being planned by NASA and other space agencies. The most ambitious of these concepts is the Habitable Worlds Observatory, or HWO. Envisioned as a flagship mission for the 2040 decade, the HWO would be a colossal space telescope specifically engineered for one overarching purpose: to find and characterize at least 25 Earth-like planets in habitable zones and search their atmospheres for signs of life. This represents a quantum leap from our current methods, moving beyond mere detection to direct, detailed analysis of other worlds. The key technology that will make this possible is a coronagraph or a starshade, an advanced instrument designed to block out the overwhelming light of a host star. Think of it as creating an artificial eclipse within the telescope itself. A coronagraph is a complex system of masks and mirrors inside the telescope that precisely cancels out the starlight, while a starshade is a separate, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of the telescope, positioning itself perfectly to cast a shadow on the scope, blotting out the star and allowing the faint, orbiting planets to shine through. With the star's glare suppressed, the HWO would capture the actual, direct light reflected off these exoplanets. This light is a goldmine of information. By splitting this light into a spectrum, scientists can read it like a barcode, identifying the specific fingerprints of molecules in the planet's atmosphere. The primary hunt will be for what astronomers call biosignatures, combinations of gases that are difficult to explain without the presence of biology. The simultaneous detection of oxygen and methane, for example, would be a monumental discovery. These gases rapidly destroy each other, so finding them together in significant quantities suggests a continuous, planet-wide source, much like the photosynthetic life on Earth that constantly replenishes our oxygen. But the journey doesn't end with HWO. Other groundbreaking missions are paving the way. The European Space Agency's Pluto, or Planetary Transits and Oscillations of Stars mission, scheduled for launch in just a few years, is designed to find and study thousands of rocky planets around Sun-like stars. Its unique focus will be on finding Earth twins with long orbital periods, the true analogues to our own world that have been so difficult to spot. Then there's the LUVOIR and Origin Space Telescope concepts, which represent even more powerful visions for the future. LUVOIR, a concept for a giant space telescope with a mirror up to 15 meters across, dwarfing even the James Webb, could not only analyze atmospheres but also map surface features of exoplanets, potentially detecting continents, oceans, and even the seasonal changes of vegetation. The Origin Space Telescope would be an enormous cold observatory specializing in the far infrared, allowing it to peer through dust clouds to study the birth of planetary systems and detect water vapor in the atmospheres of small, cool planets with unprecedented clarity. These missions represent a fundamental shift in our strategy. We are moving from a period of discovery into an era of profound characterization. the ultimate goal is to assemble a statistical census of life in our galactic neighborhood. By surveying dozens of the most promising Earth-like worlds, we can finally answer the question of whether life is a rare, fleeting phenomenon or a common, even inevitable outcome of cosmic evolution. Finding a single biosignature would be incredible, but finding a pattern discovering that life-bearing atmospheres are a recurring feature around stable stars would fundamentally reshape our understanding of our place in the universe. This next technological leap will transform these distant points of light into full-fledged worlds with known climates, weather patterns, and just maybe the unmistakable chemical signature of a living biosphere, forever changing our perspective on the cosmos and our solitary existence within it. From the scorching inner edge of the habitable zone to the frigid, tidally locked frontiers, we have witnessed a staggering gallery of worlds that defy our earthly imagination. We have wandered hypothetical landscapes under the light of 2 or even 3 suns, dived into the abyssal depths of global oceans that could swallow our entire planet, and envisioned life clinging to existence in the temperate twilight rings of eternally daylit worlds. This journey across 30 exoplanets reveals a cosmos not of barren rocks and gas giants, but a vibrant tapestry of potential habitats, each with its own unique story of gravity, light, and chemistry. The sheer diversity we have encountered from the hurricane-swept Hycean world K218b to the serene, ancient promise of Teegarden star B teaches us a fundamental truth. The universe is a master of invention, crafting environments for life from a palette far broader and more alien than we ever dared to dream just a generation ago. The profound implications of this diversity ripple far beyond astronomy. If just one of these 30 worlds, or one of the billions like them in our galaxy, were found to host even the simplest forms of life, it would represent the most monumental discovery in the entire history of human civilization. It would answer the ancient question whispered by every culture that has ever looked to the stars: we are not alone. The philosophical and scientific revolution would be absolute. We would know with certainty that life is not a singular, fragile accident confined to our pale blue dot, but a natural, cosmic phenomenon. The very definition of life itself would expand, forcing us to reconsider our place in the universe not as its sole focus, but as one voice in a vast cosmic chorus. The discovery of a single microbe on a distant world would transform biology from a science of Earth into a science of the universe, opening up entirely new branches of understanding about how life begins, evolves, and persists across the cosmos. This grand quest is accelerating at a breathtaking pace. The field of exoplanet science is moving from an era of discovery into an age of profound characterization. The James Webb Space Telescope is already peering into the atmospheres of worlds like Trappist 1e and LHS 1140b, and the next generation of observatories like the Habitable Worlds Observatory are being designed with the explicit goal of directly imaging and analyzing the air of dozens of Earth-like planets. We are on the cusp of moving from knowing that these worlds exist to understanding what they are truly like, to reading their climates, their weather, and their chemical compositions for the telltale signs of a living biosphere. The data is flowing in faster than ever before, with new candidates and groundbreaking analyses being published on a near-weekly basis, each one refining our search and bringing us closer to that epoch-making revelation. Your journey into this cosmic mystery does not have to end here. You have now become a citizen of this new frontier, armed with the knowledge of what to look for and why it matters. The search for life beyond Earth is a collective human endeavor, and you can be an active part of it. Follow the missions. Keep an eye on the latest news from NASA, the European Space Agency, and observatories around the world. The moment a biosignature is tentatively identified or a new, promising world is found, it will ripple across the globe. Share this sense of wonder, discuss these possibilities with friends and family, and nurture that innate human drive to explore and understand. The greatest discovery in history is waiting just beyond the next data point, the next transit, the next faint signal from a distant star. The universe has shown us its incredible potential. Now it is up to us to keep looking, to keep questioning, and to stay relentlessly curious about the infinite possibilities that lie hidden in